Welcome back, everyone. Today, we're diving deep into Grisha Perelman's famous paper, The Entropy Formula for the Ricci Flow and its Geometric Applications. It's a paper that not only had huge implications for geometry and topology, like helping to prove the Poincaré conjecture, but it also introduced some incredibly beautiful and powerful mathematical ideas.
Yeah, it's a real tour de force. And for this deep dive, we're gonna really try to get into the nitty-gritty of the math, for our audience who really want to understand the technical details.
Absolutely. So for those just joining us, maybe a quick recap. The paper is all about Ricci flow, which is an equation that describes how a Riemannian metric on a manifold changes over time.
Right. And the equation itself, looks deceptively simple. It's dtj2, my ball math upper time. But as you start to unpack it, you realize there's a whole universe of complexity hidden inside.
So it's saying that the rate of change of the metric at a point is proportional to the Ricci curvature at that point.
Exactly. Areas of high curvature change more rapidly, kind of like how wrinkles in space-time smooth out faster, where there's a lot of gravitational action, right?
Perfect analogy.
Oh, yeah.
Now, Richard Hamilton, who was really one of the pioneers in this field, showed that this equation has a unique solution, at least for a short time.
Yeah, for a short time at least. Starting from, any smooth metric on a closed manifold.
Okay, so we know how the movie starts, but what happens as time goes on? Does the shape always become perfectly smooth, or can things, go off the rails a bit?
Well, that's where the real fun starts, right? Sometimes the curvature can actually become infinitely large in a finite amount of time. And we call those points singularities.
So it's like our shape suddenly develops a pinch point or a tear.
Exactly. And to analyze those singularities, mathematicians use a technique called blowing up. You're essentially zooming in on the high curvature region as it forms.
So we can examine the tear, frame by frame as it's happening.
Precisely. And to understand the structure of these singularities, we turn to a special class of solutions to the Ricci flow called ancient solutions.
Ancient solutions.
Yeah, these are solutions that exist infinitely far back in time, so they can give us a glimpse into the past of the singularity, so to speak.
Wow. Okay, so they're like the prequels to our singularity movie.
Right. They tell us how things got so dramatic in the first place. And these ancient solutions played a really crucial role in Hamilton's program for proving the Thurston geometrization conjecture.
Okay, now for our listeners who might not be familiar, this geometrization conjecture basically says that any three-dimensional shape can be decomposed into pieces, each with a very specific geometric structure.
Right. Think of it like you have a set of building blocks. Each block has a certain shape, and you can build any three-manifold by gluing these blocks together in the right way.
So it's about finding the fundamental building blocks of three-dimensional shapes. And Hamilton thought that Ricci flow might be the key to actually proving this conjecture.
That's right. His program was essentially you start with any three-manifold, you let it evolve under the Ricci flow, and you carefully analyze what happens, particularly when these singularities form. If you can control these singularities, you should be able to decompose the manifold into these geometric pieces that Thurston predicted.
So it's like the Ricci flow is a sculptor chiseling away at our shape to reveal its underlying structure.
Exactly. But controlling those singularities is where things get really tricky. One of the key challenges is understanding how something called the injectivity radius of the manifold changes under the Ricci flow.
Yes, the injectivity radius. It's essentially a measure of how crumpled the geometry is on a point, right?
Yeah. The smaller the radius, the more the shape is folding in on itself. And for Hamilton's program to work, we need to show that the injectivity radius doesn't shrink too fast under the Ricci flow, because if it collapses too quickly, we lose control of the geometry and can't really analyze those singularities properly.
So it's like trying to carve a delicate sculpture with a hammer. If you hit it too hard, you just shatter it. And Perelman's paper provides a way to prevent this shattering, right?
Right. He introduces this, what we call the no local collapsing theorem. It says that under certain conditions, the injectivity radius can't shrink faster than a certain rate.
So it prevents the geometry from becoming too wild too quickly. That's fascinating. But before we get into that, you mentioned something earlier about a connection between Ricci flow and something called the renormalization group flow. That's from physics, right?
Yeah, it is. It's a really interesting connection. In quantum field theory, the renormalization group flow, or RG flow, describes how physical theories change as we look at them at different scales. And what's surprising is that Ricci flow which is a purely geometric concept, has an analogous interpretation.
So time, in our Ricci flow movie, is like a scale parameter in physics.
Exactly. As time progresses in Ricci flow, it's like we're zooming in with, a more powerful microscope, seeing the shape at smaller and smaller scales. And what appears far apart at a large scale might become very close or even connected at smaller scales.
It's like our shape has these hidden microscopic structures that only reveal themselves as we go deeper into the Ricci flow.
That's a great way to think about it. And this connection with RG flow led mathematicians to suspect that Ricci flow might actually have what we call a gradient-like nature, much like how physical systems tend to minimize their energy.
So they suspected that Ricci flow is also trying to minimize something, some sort of geometric energy.
Precisely. And this is where Perelman's entropy formula comes in. He introduces a specific functional, we'll call it F, and he shows that Ricci flow can actually be interpreted as the gradient flow of this functional.
So F is like our geometric energy landscape, and the Ricci flow is like a ball rolling down this landscape, seeking the lowest point.
That's a great analogy. Now, F itself is defined for both a Riemannian metric and a scalar function. And it turns out that the gradient of F with respect to the metric is a specific combination of the Ricci curvature and the derivatives of that scalar function.
So we can picture F as this landscape, and its gradient tells us the steepest descent direction, the direction that ball would roll. But you mentioned different choices for this scalar function. Does that change the energy landscape in a meaningful way?
It's a great question, and it leads to a really interesting insight. Different choices of the scalar function actually lead to the same Ricci flow up to a diffeomorphism.
Okay, so the underlying flow is the same, but the coordinates on our energy landscape might change. It's fascinating. But where do we go from here?
Well, next we need to look at some of the key results that Perelman proves using this gradient flow interpretation, starting with proposition 1.2.
So proposition 1.2, what does that tell us?
Essentially, it establishes an upper bound on the value of f at the initial time of the flow.
So it's like setting a limit on how high up the hill we can place that ball.
Exactly. And the proof involves deriving the evolution equations for the gradient flow of f. These equations describe how both the metric and the scalar function change over time as they follow the steepest descent path on that f landscape.
Okay, so we're mapping the trajectory of the ball frame by frame.
Right. And by analyzing these evolution equations, you can derive an inequality that relates the rate of change of f to the value of f itself. And this inequality ultimately leads to the upper bound that's stated in proposition 1.2.
Clever. So he's using the dynamics of the flow to constrain the initial energy. Now, you mentioned the Bochner-Lechnerowicz formulas earlier. How do those fit into this picture?
Yeah, the Bochner-Lechnerowicz formulas are these really powerful identities in Riemannian geometry that relate the Laplacian of a tensor field to its curvature. And they're typically formulated using the Riemannian volume form as the measure on the manifold.
Right, the volume form is like the natural way to measure volume on a curved space.
Exactly. But Perelman observed that if you replace the volume form with a different measure, the Bochner-Lechnerowicz formulas change in a very specific way. And the modified formulas actually involve terms that appear in the definition of our functional f.
So changing the measure is like putting on a special pair of glasses that highlights the features of the landscape that are important for understanding the flow.
That's a great way to put it. It's like we're focusing our attention on the parts that really matter.
Okay, we've gone from smoothing shapes to energy landscapes and modified Bochner-Lechnerowicz formulas. This is pretty amazing stuff. But now, about that term no breathers, what does that even mean in this context?
Yes, no breathers. That's where we really start to see the power of this gradient flow perspective. To understand breathers, we need to think about Ricci flow as a dynamical system.
All right, let's do that.
Yeah.
Imagine we have this space of all possible Riemannian metrics on a given shape. The Ricci flow equation tells us how each metric evolves over time.
Right, exactly. And a breather is a solution where the shape essentially breathes. Its metric expands and contracts periodically over time.
So the shape is pulsating, growing, and shrinking, but in a repeating pattern.
Yeah, that's a good way to visualize it. Now, Perelman's no-breathers theorem says that for a closed manifold, there are no non-trivial breathers except for Ricci solitons.
Ricci solitons, right. Aren't those the special solutions where the shape basically flows into itself?
Exactly. They're like the fixed points of the Ricci flow, while breathers are like these periodic orbits. And Perelman's theorem is saying that the only allowed loops in our Ricci flow movie are these special Soliton solutions.
That's a pretty strong statement about the long-term behavior of Ricci flow. And you said the proof relies on the gradient flow interpretation.
It does. Perelman's argument is really elegant. He analyzes the steady expanding and shrinking breather cases separately. And for each case, he uses the monotonicity of carefully chosen quantity to rule out the existence of non-trivial breathers.
Okay, so we need to unpack these monotonicity arguments. But before we get into the details of each case, maybe it's a good time for our listeners to take a little break and grab a coffee. We'll pick up right where we left off and really delve into the heart of the no-breathers theorem. Welcome back, everyone. So we've been exploring these incredible ideas in Perelman's paper, like the gradient flow nature of Ricci flow and the no-breathers theorem. Now let's dive into these no-local collapsing theorems. They seem pretty crucial for understanding how the geometry behaves, especially when we get near those singularities.
Yeah, absolutely. Local collapsing is essentially a situation where the injectivity radius shrinks much faster than you would expect based on the curvature. Imagine a balloon deflating, but really unevenly. Some parts are shrinking super fast, while others stay pretty much the same.
Right, so the geometry is getting distorted in a very particular way. Why is this a problem for Ricci flow?
Well, if that happens, if we have this local collapsing, we kind of lose control of the geometry, right? The injectivity radius is like our safety margin. If it collapses, things can get too wild to really analyze effectively. And that makes it much harder to understand those singularities and actually implement Hamilton's program.
Okay, so these no local collapsing theorems are kind of like guardrails preventing the geometry from going off the rails too much. So how do they work?
Right. So Perelman actually gives us a few different theorems, each with, slightly different conditions and conclusions. Let's start with theorem 4.1, which deals with smooth solutions to the Ricci flow on a closed manifold over a finite time interval. Basically, it says that local collapsing cannot occur at the final time.
So if we run the Ricci flow for a fixed amount of time, we're guaranteed that there won't be any local collapsing at the very end. How do we know that?
He uses a really clever proof by contradiction. Remember that monotonicity formula for the W functional that we talked about earlier?
Yeah, I remember. W can't decrease along the Ricci flow.
Exactly. So let's assume, just for the sake of argument, that local collapsing does happen at the final time.
Okay, let's assume that.
Then what Perelman does is he constructs a specific function, phi, and a scale parameter tau, such that the value of W at this final time is actually less than its initial value.
Wait a minute, but that would contradict the monotonicity formula? Right. We said W can't decrease.
Exactly. That's the contradiction. If local collapsing were to happen, we could make WE decrease, which breaks our fundamental monotonicity principle.
Ah, I see. It's like setting a trap. If local collapsing tries to sneak in, it sets off this chain reaction that violates one of our key rules.
Precisely. And that contradiction forces us to, throw out our assumption of local collapsing, which proves theorem 4.1.
Okay, that's pretty neat. So theorem 4.1 rules out local collapsing at the final time for those finite time solutions. But what about solutions that exist for a longer time or even, infinitely long?
That's where things get even more interesting. To handle those cases, Perelman introduces this new concept, kappa non-collapsing. It's a way to quantify how much room we have in the geometry, even as the metric is changing.
Kappa non-collapsing. Okay, can you unpack that a little bit?
Sure. Imagine you have a ball, right? A ball of a certain radius centered at some point on our manifold. Kappa non-collapsing basically says that if the curvature within that ball is, under control, it's not too wild, then the volume of that ball can't shrink below a certain threshold. And this parameter, kappa, is what controls this threshold.
So it's like a lower bound on how much the shape can squeeze itself, right? It prevents it from completely collapsing in any given region.
That's a great way to think about it. And what Perelman shows is that this kappa non-collapsing property is actually closely tied to the absence of local collapsing. He proves this corollary 4.2, which says that under certain conditions, a solution to the Ricci flow on a closed manifold is kappa non-collapsed for some positive kappa.
So this corollary guarantees that we have a certain amount of breathing room, geometrically speaking. It prevents the shape from just, crumpling up into nothing. But how does this all connect back to theorem 4.1 and the whole no local collapsing idea?
Well, corollary 4.2 actually follows from theorem 4.1, along with this really powerful convergence theorem by Hamilton. This convergence theorem tells us that if we have a sequence of Ricci flows where the curvature and injectivity radius are kind of well behaved, then we can always extract a subsequence that converges to a new Ricci flow.
So it's like taking a limit of those evolving shapes. If the shapes in the sequence are nice, then the limit will also be a nice shape.
Exactly. And by combining theorem 4.1, which rules out that local collapsing at a finite time, with this convergence theorem, Perelman is able to show that solutions on closed manifolds must be kappa non-collapsed.
Okay, so he's built these theorems that prevent our shapes from collapsing too much under the Ricci flow, even over, long periods. This seems really essential for understanding those singularities. But earlier, you mentioned this surprising connection between Ricci flow and statistical mechanics. Can we talk a bit more about that?
Yeah, absolutely. It's one of the most fascinating parts of Perelman's work, in my opinion. He draws this really deep analogy between certain quantities in Ricci flow and concepts from statistical mechanics, particularly the canonical ensemble.
A canonical ensemble. That sounds familiar from thermodynamics. Can you remind me what that is?
Sure. Imagine you have a system, right? And it's in contact with this heat reservoir at a fixed temperature. The canonical ensemble basically describes the statistical properties of that system as it's exchanging energy with the reservoir.
Okay, so it's a system trying to reach, like, thermal equilibrium with its surroundings. But how does this relate to Ricci flow? I mean, we're talking about the evolution of shapes, not heat and temperature.
Right, but here's the amazing thing. Perelman shows that the functional W, the one we use to analyze those shrinking breathers, has a direct counterpart in statistical mechanics, entropy. And he demonstrates that the partition function, average energy, entropy, and even things like fluctuation in the canonical ensemble, they all have these analogs in the context of Ricci flow.
Hold on. So you're saying that, like, these abstract mathematical quantities in Ricci flow correspond to actual physical concepts like energy and entropy?
That's exactly right. It's like he's found this hidden dictionary that translates between the language of geometry and the language of physics.
Okay, I'm definitely intrigued now. Can you give us some specific examples of these translations?
Sure. So for instance, the partition function in statistical mechanics, that corresponds to a certain integral involving that function f in our W functional. And the average energy that has a counterpart in Ricci flow involving the scalar curvature and the derivatives of f, and maybe the most striking one, the entropy actually corresponds to the negative of our W functional.
So minimizing WA in Ricci flow is like maximizing entropy in a physical system. That's pretty mind-blowing.
Yeah, it is. And this analogy gives us a whole new perspective on Ricci flow. For example, it suggests that ancient solutions, the ones that exist infinitely far back in time, might be characterized by having bounded entropy, just like a system that's in equilibrium.
So it's like those ancient solutions represent states of, like, maximum geometric disorder.
Exactly. Now, of course, it's important to remember that this is an analogy. We're not actually dealing with heat and temperature in Ricci flow.
Right, right. But it's a really powerful analogy, isn't it? It allows us to use our intuition from physics to understand this, very abstract geometric process.
Absolutely. So we've gone from smoothing out shapes to exploring these energy landscapes, and now we're connecting geometry to the statistical behavior of physical systems. Where does Perelman take us next?
Yeah, where do we go from here?
Well, next he delves into a more abstract realm, Riemannian geometry in potentially infinite dimensions.
Infinite dimensions. Okay, that sounds a little intimidating. What's the motivation for going there?
It's actually inspired by that statistical mechanics analogy we were just talking about. Remember how we said it suggests we can think of our evolving shape as being embedded in this larger space, kind of like a thermostat that's governing its behavior?
Yeah, I remember.
Well, this larger space is actually constructed using the formalism of Riemannian geometry, but with a twist, it can have infinitely many dimensions.
Okay, so we're stepping outside of the familiar world of three dimensions. But why do we need to do that? What does it allow us to do?
Well, it allows Perelman to give a geometric interpretation to these formal expressions that arise in the statistical mechanics analogy. He constructs a specific metric on this larger space and shows that its curvature components are actually related to Hamilton's matrix-Harnack expressions.
Hamilton's matrix-Harnack expressions. Refresh my memory on those.
Right. Those are these inequalities that describe how curvature evolves under the Ricci flow. They play a really important role in understanding how those singularities form.
So we're translating the language of, like, entropy and energy into the language of curvature and metrics, but in this in this much more abstract, infinite dimensional space.
Exactly. And this geometric perspective actually has some really interesting consequences. For instance, Perelman shows that the heat and conjugate heat equations on our original manifold, they can actually be viewed as Laplace equations on this larger space.
Laplace equations. Those are like fundamental equations in physics. They describe how things like heat or electric potential spread out. So we're connecting the flow of heat on our shape to the geometry of this much larger space.
You got it. And this connection actually leads to another remarkable result, a monotonicity formula for something called the reduced volume.
You're reduced to volume. Okay, another new concept. Tell me about it.
So the reduced volume is a quantity that measures the volume of our shape, but relative to this special distance function that's defined using the Ricci flow. It's kind of like, imagine you're measuring the volume of a balloon as it's deflating, but you're using a ruler that's shrinking along with the balloon.
Okay, so we're taking into account how the metric itself is changing as we're measuring the volume. That makes sense. But what's so special about this reduced volume?
Well, Perelman proves that the reduced volume is actually non-decreasing as we go backward in time along the Ricci flow.
Non-decreasing as we go backward. That's kind of counterintuitive.
Yeah, it might seem strange. But remember, we're working with this kind of time-reversed perspective in this part of the paper, and this monotonicity formula turns out to be incredibly powerful for analyzing how the Ricci flow behaves, especially when we're studying those ancient solutions.
Okay, so we have this reduced volume, and it doesn't decrease as we go back in time. But how does Perelman actually prove this monotonicity?
His proof actually takes us on a journey through what's called comparison geometry, which is this field of mathematics that compares geometric quantities on different spaces. He introduces a modified notion of length for curves, which he calls the L length, and this L length takes into account the evolution of the metric under the Ricci flow.
So instead of measuring distances with the usual metric, we're using the special L length that incorporates the flow.
Exactly. And this leads to a modified version of the geodesic equation, which is the equation that describes, the shortest paths in a curved space. Perelman derives a special equation for these L geodesics and uses it to analyze how the reduced volume behaves.
So we're exploring shortest paths on a surface where the distances themselves are changing over time. This is pretty abstract stuff.
It is, but it's incredibly powerful. By carefully studying these L geodesics, Perelman derives a series of inequalities that ultimately lead to the proof that the reduced volume is monotone.
Wow, it sounds like a real tour de force of mathematical reasoning.
It really is. And this monotonicity formula, together with that concept of kappa non-collapsing we talked about, leads to another version of the no local collapsing theorem, Theorem 8.2.
Another one. What's different about this one?
It provides even stronger control over the geometry, but under slightly different assumptions. Essentially, it guarantees that if a solution satisfies certain curvature and volume conditions at some initial time, then it can't be kappa collapsed at later times within a certain region of spacetime.
So it's like an extended safety net, preventing the injectivity radius from collapsing for a longer period in a particular region.
Exactly. And this theorem is crucial for analyzing what happens to the Ricci flow near those singularities.
Okay, so we've talked about no breathers, no local collapsing, this amazing connection to statistical mechanics. What else does Perelman explore in this incredible paper?
Well, he actually goes on to delve deeper into the properties of the conjugate heat equation, and he derives this really powerful differential Harnack inequality for its solutions. This inequality allows us to compare the values of that function, f, the one that's part of the WH functional, at different points in times, taking into account the curvature and how the metric is evolving.
So we're back to comparing things in our evolving geometry, but this time we're focusing on the solutions to the conjugate heat equation. What's so important about this differential Harnack inequality?
Well, it has a few really important consequences. First, it actually gives us another way to prove that monotonicity formula for WO, which gives us more insight into why this quantity is so important. Second, it leads to a beautiful characterization of Ricci flow based on how these, what we call fundamental solutions to the conjugate heat equation behave.
A characterization of Ricci flow. What do you mean by that?
Well, Perelman shows that the specific way these fundamental solutions evolve under the Ricci flow, it's actually unique to Ricci flow. No other geometric flow has this precise property. It's like a fingerprint that identifies Ricci flow amongst all other flows.
That's pretty amazing. So the conjugate heat equation not only gives us tools to analyze Ricci flow, but it also captures its very essence.
Exactly. And this deep connection actually leads to another major result, the pseudo-locality theorem, theorem 10.1.
Pseudo-locality. Okay, break that one down for me.
All right, so imagine you have a region of our shape that starts off almost Euclidean, meaning it has very small curvature. The pseudo-locality theorem basically says that this region will remain almost Euclidean for a short time under the Ricci flow, regardless of what happens far away.
So it's like this locality principle. Changes in one part of the shape don't immediately affect distant regions, at least not for a little while. Even if things are going crazy somewhere else, this calm region can stay calm.
Exactly. And what's really remarkable about this theorem is that it holds even if the curvature in other parts of the shape becomes very large. It's like a shield that protects this almost Euclidean region from those distant storms.
That sounds incredibly powerful. How does he actually prove that this shielding effect works?
Well, he uses that differential Harnack inequality that we talked about, the one for the conjugate heat equation, to control how fast the curvature can grow in this almost Euclidean region. He constructs this special function and uses a really clever cutoff argument to isolate this region and then analyzes its behavior.
So he's like building a mathematical firewall to prevent the chaos from spreading too quickly.
That's a great analogy. And the pseudo-locality theorem, along with all of these other results that we've been discussing, they really provide us with this deep understanding of how singularities form and how they propagate under the Ricci flow.
Wow, this deep dive has been quite a journey. We've gone from smoothing out shapes to proving that certain breathing patterns are forbidden. We've explored connections to statistical mechanics and even ventured into infinite dimensions. I'm really impressed by the depth and the beauty of Perelman's work.
It's truly a landmark achievement, and it's had an immeasurable impact on the world of mathematics. But there's one final section of the paper that I think deserves some attention. It's where Perelman focuses on ancient solutions in dimension 3 that have non-negative curvature operator and bounded entropy.
So back to those ancient solutions, the prequels to singularity formation, right? What does Perelman tell us about them?
Well, he proves that under these specific conditions, ancient solutions can actually be rescaled and blown down to converge to gradient shrinking solitons.
Gradient shrinking solitons, the fixed points of the Ricci flow. So even though these ancient solutions can be really complex, when we zoom out and look at them from a larger perspective, they ultimately approach these simpler, more symmetrical forms.
Exactly. And Perelman actually uses this knowledge to then go and analyze how the Ricci flow behaves under even more general curvature conditions, specifically what he calls almost non-negative curvature in dimension 3.
Almost non-negative curvature. So it's like we're relaxing that previous condition a little bit.
Right. We're allowing the curvature to dip slightly into negative territory, but requiring it to stay mostly positive. And Perelman shows that solutions with this almost non-negative curvature, they can actually be locally approximated by ancient solutions.
So even if the curvature isn't perfectly non-negative, we can still use the tools that we've developed for ancient solutions to understand the flow.
Precisely. And this approximation technique allows Perelman to derive all sorts of really powerful estimates for the curvature and the volume. And these estimates ultimately lead to a description of the global picture of the Ricci flow in dimension 3.
Global picture. It sounds like the grand finale of Perelman's masterpiece. What does this picture look like?
Well, he proves this really amazing theorem, the decomposition theorem. It says that for large enough times, any solution to the Ricci flow on a closed three-manifold, it can actually be decomposed into a thick part and a thin part. The thick part, it has controlled curvature and volume, and it either converges to what we call a hyperbolic manifold, or it eventually just disappears. The thin part, on the other hand, it collapses in a controlled way.
So Perelman is essentially giving us a roadmap for how the Ricci flow behaves in the long run. Either the shape breaks down into pieces that converge to, familiar geometric structures, or it collapses in a way that we can understand.
That's a great summary. And this decomposition theorem, combined with Perelman's analysis of the singularities and that surgery process that we talked about earlier, it actually provides the framework for proving the Poincaré and geometrization conjectures.
Incredible. We've gone from just smoothing out shapes to tackling one of the biggest results in the history of mathematics. This deep dive into Perelman's paper has been a truly mind-blowing experience.
It really speaks to the power of human ingenuity and the elegance of mathematical reasoning.
Couldn't have said it better myself. Thank you so much for guiding us through this fascinating world.
It's been my pleasure, and I hope our listeners are feeling inspired to maybe explore some of these ideas further on their own.
Absolutely. Until next time, keep those minds curious and never stop exploring the beauty and power of mathematics. All right, let's dive deep into some serious mathematics. We're going to be tackling Grisha Perelman's work on the Ricci flow,
Oh, fantastic.
specifically his entropy formula and the implications. This stuff is really dense,
Yeah.
but trust me, it's an incredible journey.
Yeah, Perelman's work is really groundbreaking.
Yeah,
It's like he found a new language to describe the evolution of geometric shapes.
exactly. And so we all know that the Ricci flow is this equation that describes how the geometry of a manifold
Right.
changes over time.
Yes.
Think of it like watching a lump of clay slowly morphing and
Yeah.
smoothing out.
Exactly. And Perelman's entropy formula
Yeah.
gives us a way to measure how organized the shape becomes during this process.
Okay.
It's like having a ruler for geometric complexity.
I'm intrigued, but we're talking about Perelman here.
Yeah.
And his work is notoriously complex.
Yes, very much so.
So let's break down his paper, focusing on his entropy formula, and extract those key insights.
Okay, sounds good.
And we're going to start with the idea of the Ricci flow as a gradient flow.
Okay, great starting point.
Okay.
So think of a ball rolling down a hill.
Mm-hmm.
It naturally seeks the lowest point, right?
Right.
Similarly, the Ricci flow can be viewed as a downhill process
Okay.
in the space of Riemannian metrics.
Right.
It's always seeking to minimize a certain energy functional.
And this energy is directly related to Perelman's entropy formula.
Precisely. Perelman defined a functional,
Okay.
often denoted by W.
Okay.
It depends on the metric, a scaling factor, and a function.
Okay.
This functional, when minimized, gives us the entropy.
Okay, so the Ricci flow is trying to minimize this W functional,
Yes.
which in turn minimizes the entropy, making the shape more, quote, organized over time.
Exactly. And the way this minimization happens
Right.
is captured by the fact that the change in the W functional along the Ricci flow is always non-negative.
Mm-hmm.
It's like a mathematical guarantee that the entropy can never decrease.
That's fascinating. So as the Ricci flow smooths out the geometry,
Yes.
it's also pushing the entropy downhill towards a minimum.
Exactly.
What are the implications of this?
Well, one key consequence is the no-breathers theorem.
Okay.
This theorem essentially says that under the Ricci flow, a shape cannot periodically repeat its form.
Wait, so shape can't, like, breathe in and out geometrically speaking?
Exactly. Once a bump is smoothed out by the Ricci flow,
Right.
it's gone for good.
Wow.
No geometric heartbeats allowed.
That's incredible. So the Ricci flow has this inherent directionality,
Yeah.
always pushing towards greater simplicity and uniformity.
Precisely. And the no-breathers theorem is a direct consequence of the non-decreasing nature of Perelman's entropy.
Right.
It's a testament to how a seemingly abstract concept like entropy
Yeah.
can have profound implications for the behavior of geometric shapes.
Okay, I'm starting to get a sense of the power of this entropy concept.
Good.
But does this relentless smoothing mean that a shape can just shrink down to nothing under the Ricci flow?
That's a great question.
Yeah.
And it leads us to another of Perelman's key results.
Okay.
The no local collapsing theorem.
Okay.
This theorem states that there's a limit to how much a shape can shrink in a small region,
Oh.
even as the overall geometry smooths out.
So there's a kind of safety net built into the Ricci flow, preventing catastrophic collapses.
Exactly. Imagine you're looking at a shape evolving under the Ricci flow
Okay.
through a microscope with a fixed zoom level.
Right.
No matter how much the shape shrinks overall,
Okay.
the no local collapsing theorem guarantees that you'll always be able to see at least some part of it within your field of view.
That's a great way to visualize it.
Yeah.
So we had this balance. The Ricci flow smooths things out,
Yes.
but also prevents them from disappearing completely.
Right.
How does entropy fit into this picture?
The entropy plays a crucial role in establishing the no local collapsing theorem.
Right.
It acts as a kind of mathematical watchdog,
Okay.
ensuring that the geometry doesn't misbehave.
Can you elaborate on that? How does entropy act as a watchdog?
Well, remember the W functional we discussed earlier?
Yes.
To prove the no local collapsing theorem,
Right.
we analyzed the behavior of this functional on a sequence of shrinking balls within the manifold.
Okay.
If the volume of these balls were to collapse too quickly,
Right.
it would lead to a contradiction with the non-decreasing property of the W functional.
Ah, so the entropy through the W functional imposes constraints on how quickly the geometry can shrink.
Yes.
It's like a built-in safeguard against excessive collapse.
Exactly. And this connection between entropy and geometric stability is one of the most beautiful aspects of Perelman's work.
This is amazing. It seems like entropy is this hidden hand guiding the Ricci flow.
Yes.
Ensuring it smooths things out without any wild collapses or time loops.
Yeah.
What's next on our Perelman adventure?
Let's shift gears and explore comparison geometry and a remarkable tool called reduced volume. This will give us a way to analyze how the shape changes at different scales under the Ricci flow.
Sounds intriguing. So we're going beyond just looking at the shape itself and zooming in and out, so to speak.
Precisely. The reduced volume gives us a way to compare the evolving geometry of our shape to that of a model solution, like a shrinking sphere. It's like having a special lens that lets us see the evolution from different perspectives.
Okay, so we're comparing our evolving shape to these simpler model solutions.
Yes.
How does that help us understand the Ricci flow?
Well, the reduced volume has this remarkable property.
Okay.
It actually decreases under the Ricci flow.
Hold on.
Yeah.
Didn't we say that the entropy is non-decreasing?
Yes, that's correct.
And isn't the reduced volume also a measure of how spread out or disorganized the shape is?
Yes, you're right.
Are these two ideas in conflict?
Excellent question. You're right. The entropy is non-decreasing, and the reduced volume is indeed a measure of disorder. However, the key difference is that the reduced volume incorporates information about the evolving metric, while the entropy is a more global quantity.
Okay, I see the distinction. The reduced volume is like a local snapshot of the disorder at a particular scale.
Exactly.
While the entropy is a measure of the overall disorder of the entire system.
Exactly. And even though the reduced volume can decrease locally,
the
overall entropy of the system never goes down.
Okay.
It's another testament to the balancing act of the Ricci flow.
So we have these two complementary perspectives. The entropy giving us a global view of the system's order.
Yes.
And the reduced volume providing a localized picture of how the geometry is smoothing out at different scales.
Precisely. And by combining these perspectives, we gain a deeper understanding of the intricate dynamics of the Ricci flow.
This is mind-blowing. It's like we've discovered a hidden language of geometry.
I agree.
And Perelman's work is the key to deciphering it.
Yes.
Speaking of mysteries, I have a question. We've talked about this multi-scale smoothing effect of the Ricci flow.
Right.
But is it possible for chaotic behavior at a very small scale to instantly spill over and disrupt the larger scale structure?
That's a fantastic question.
Yeah.
And it brings us to another groundbreaking result by Perelman.
Okay.
The pseudo-locality theorem.
Right.
This theorem provides a sense of stability, ensuring that small-scale chaos doesn't instantly translate into large-scale disasters.
So even if there's some crazy curvature happening at a tiny scale, the larger scale features can remain relatively smooth for a while.
Precisely. It's like saying that even if there's a tiny ripple in the fabric of space-time, it won't instantly unravel the entire universe.
That's a relief.
Yeah.
But how does Perelman manage to establish this mathematical shield against chaos?
It's a rather intricate proof.
Okay.
But the core idea is to carefully analyze the evolution of curvature under the Ricci flow. And show that curvature can only propagate at a finite speed. He used a clever combination of techniques, including his differential Harnack inequality for the conjugate heat equation.
Wow.
And a delicate choice of cutoff functions to control the spread of curvature.
So even though the Ricci flow is a nonlinear equation, Perelman managed to impose a speed limit on the propagation of curvature.
Exactly.
That's incredible.
It truly is. It's a testament to his deep understanding of the flow's behavior and his mastery of mathematical tools.
This is all very exciting, but I'm starting to feel a bit overwhelmed.
I understand.
Is there a way to connect all these ideas? Entropy, no breathers, no collapsing, reduced volume, and pseudo-locality into a more unified picture.
That's a great point.
Yeah.
We've covered a lot of ground.
We have.
It might be helpful to think about the Ricci flow from a comparison geometry perspective.
Okay.
This viewpoint allows us to relate the evolving geometry of the manifold
Right.
to a more familiar static setting.
Okay, so how do we bridge the gap between the dynamic world of the Ricci flow and the static world of comparison geometry?
The key is to introduce a new concept,
Yep.
the L length of curves.
Okay.
Instead of measuring the length of a curve using the evolving metric,
Right.
we consider a modified length called the L length, which takes into account the curvature along the curve as the metric evolves.
Interesting. So we're incorporating the cost of moving through a curved space-time
Exactly.
as it changes over time.
Right.
Like factoring in the dynamic nature of the geometry.
Exactly. And this L length allows us to define
Right.
L geodesics,
Okay.
which are curves that minimize the L length between 2 points.
Sure.
Think of them as the straightest possible paths in this evolving curved world.
So instead of the usual geodesics, which are determined by the metric at a single moment in time,
Yes.
these L geodesics are sensitive to the way the metric is changing.
Precisely. And by analyzing these L geodesics and their properties,
Okay.
we gain deep insights into the behavior of the Ricci flow.
What kind of insights? How does this L geometry help us understand the Ricci flow?
Well, for starters, it
Yeah.
leads to a powerful comparison theorem,
Okay.
just as in classical Riemannian geometry, where we compare the geometry of a manifold to that of a model space, like Euclidean space, or a sphere
Right.
in the setting of Ricci flow.
Yeah.
We can compare the evolving geometry to that of a model solution,
Yeah.
like a shrinking sphere or a steady soliton.
I see. So by understanding how L geodesics behave in these model solutions,
Yes.
we can infer things about how they behave in our more complicated evolving manifold.
Exactly. And this leads to all sorts of remarkable results,
Yeah.
including estimates on the growth of curvature,
Okay.
control over the injectivity radius, and a deeper understanding of singularity formation.
This is fascinating. It's like we've built a bridge between the dynamic world of the Ricci flow
Yes.
and the more familiar world of static geometry.
Exactly.
And this bridge is paved with L geodesics.
You got it. And this bridge allows us to transport powerful tools and techniques from classical Riemannian geometry into the realm of Ricci flow, enriching our understanding of this fascinating subject.
This is incredible. We've uncovered so many layers of Perelman's work.
Yes.
From the entropy formula to the no local collapsing theorem.
Right.
And now this elegant connection to comparison geometry.
Indeed.
But before we wrap up this part of our deep dive,
Okay.
I'm curious about the specific examples of those ancient solutions
Of course.
that serve as our models in this L geometric world.
In dimension 3, one of the most important examples is the round shrinking sphere.
Okay.
As its name suggests, it's a sphere whose radius decreases uniformly over time until it collapses to a point.
Right.
Another important example is the round cylinder, which
Okay.
maintains its shape while its radius shrinks to 0.
Okay, so these are like the building blocks of ancient solutions in 3 dimensions.
Exactly. And Perelman showed that any non-compact ancient solution in dimension 3
Satisfy certain reasonable conditions.
Okay.
Must actually look like a round cylinder, at least outside a compact set.
Wow.
It's a remarkable rigidity result that highlights the special nature of these ancient solutions.
So if we zoom out far enough, any reasonable non-compact ancient solution in 3 dimensions
Yes.
will eventually resemble a shrinking cylinder.
Precisely.
Yeah.
And this geometric insight has profound implications for understanding singularity formation in the Ricci flow.
This is remarkable. It's like the Ricci flow, given enough time,
Yeah.
will always try to shape the geometry into these simple canonical forms.
That's a great way to put it.
Yeah.
And this drive towards simplicity is one of the most captivating aspects of the Ricci flow.
Professor, this is absolutely mind-blowing. We've journeyed from the abstract world of entropy
Yes.
to the concrete world of geometric surgery and the grand vision of Thurston's geometrization conjecture.
Exactly.
I'm starting to appreciate the depth and beauty of Perelman's work.
It is truly beautiful and profound work.
And we've only just begun to explore its richness.
Well, I'm eager to continue our exploration
Sure.
in the next part of our deep dive.
Okay.
Can we delve into the details of this thick-thin decomposition
Absolutely.
and how it helps us classify three manifolds.
Absolutely. We'll see how Perelman's work allows us to identify the regions of high curvature, where the
Okay.
geometry is thin, and the regions of low curvature, where the geometry is thick,
Right.
and how this dichotomy leads to a complete understanding of three-dimensional topology.
I can't wait. Until then, keep those brain gears turning. The world of mathematics is full of fascinating discoveries just waiting to be explored.
Very true.
Welcome back to our deep dive into the fascinating world of Ricci flow and Perelman's entropy formula. In the last part, we explored some key concepts like entropy, no breathers, no collapsing, and even touched upon the intriguing realm of L geometry. Now we're going to venture further down the rabbit hole and explore how these ideas come together to paint a global picture of the Ricci flow in 3 dimensions.
Yes, it's remarkable how these seemingly abstract concepts have such profound implications for our understanding of geometry and topology.
Okay, Professor, I'm ready to go deeper.
Yeah.
We left off talking about ancient solutions and their importance as models for understanding the long-term behavior of the Ricci flow. You mentioned something about almost non-negative curvature. What exactly does that mean?
That's a crucial concept for understanding Perelman's breakthroughs. In reality, most geometric shapes don't have perfectly non-negative curvature. Think of a crumpled piece of paper. It has regions of positive, negative, and zero curvature all mixed together.
Right, it's not perfectly smooth. So when we talk about almost non-negative curvature, are we allowing for a bit of negative curvature to exist?
Exactly. Almost non-negative curvature means we allow a small amount of negative curvature, but it's controlled in a specific way. More precisely, we say a solution to the Ricci flow has almost non-negative curvature if its curvature tensor, denoted by rhyme, satisfies the inequality. Rmx to Rs, where fourth is the special function that decays to zero as its input gets larger.
Okay, let's unpack that. R is the curvature tensor, which tells us how the space is curved at each point. And R is the scalar curvature, which is like an average curvature. What's the role of this psi function?
The function is the key to controlling the negative curvature. As the scalar curvature R gets large, becomes very small, ensuring that the allowed amount of negative curvature is tiny compared to the positive curvature.
So that's saying a little bit of negative curvature is okay, but only in regions where the positive curvature is already dominant.
That's a great way to put it. This condition prevents the negative curvature from having too much influence, allowing us to still leverage the tools developed for manifolds with non-negative curvature.
I see. Almost non-negative curvature is like a realistic compromise, acknowledging that perfect smoothness is rare, but still imposing enough structure to make progress. But why is this concept so important for understanding the Ricci flow in 3 dimensions?
It turns out that in 3 dimensions, there's a deep connection between almost non-negative curvature and the formation of singularities. Perelman proved a remarkable theorem showing that if a solution to the Ricci flow on a closed 3-manifold becomes singular, then the regions of high curvature must resemble the ancient solutions we talked about earlier, shrinking spheres, cylinders, or their quotients.
So even when things get really wild and the curvature blows up, there's still this underlying order dictated by these special ancient solutions. It's like there's a hidden blueprint guiding the chaos.
That's a great way to think about it. And this order allows us to perform a kind of surgery on the solution, cutting out the singular regions and replacing them with smooth caps, thereby extending the Ricci flow past the singularity.
Wait, we can perform surgery on geometric shapes? That sounds almost too good to be true.
It might sound strange, but it's a powerful technique. Imagine a balloon with a sharp spike. You can carefully cut off the tip of the spike and smoothly patch up the hole, resulting in a smoother balloon.
Okay, I can visualize that. But how do we know where to cut and what to patch with in the context of the Ricci flow?
That's where the almost non-negative curvature comes in. Perelman's theorem tells us that the singular regions will have a very specific geometric structure resembling those ancient solutions. So we know exactly what to cut out and how to smoothly patch things up.
This is incredible. So even when the Ricci flow encounters a singularity, we can use our knowledge of these ancient solutions to repair the geometry and keep the flow going.
Exactly. And by repeatedly performing these surgeries, we can extend the Ricci flow for all time, even in the presence of singularities.
This is mind-blowing. It's like we found a way to navigate the turbulent waters of singularity formation and reach the calm shores of a long-term solution.
Indeed. And this ability to extend the Ricci flow through singularities is precisely what makes it such a powerful tool for understanding the topology of 3 manifolds. It's like having a map that guides us through even the most treacherous terrain.
Professor, this is all very exciting, but I'm starting to get a little lost in the details. Can you step back and give us a sense of the big picture? What does this all mean for understanding the geometry and topology of three manifolds?
Absolutely. Perelman's work on the Ricci flow culminates in a proof of Thurston's geometrization conjecture, which is a grand vision for classifying all three-dimensional manifolds. It's like having a periodic table for three-dimensional shapes, organizing them based on their fundamental geometric properties.
Okay, that sounds ambitious. So how does the Ricci flow help us build this periodic table of shapes?
Imagine you start with any three-dimensional manifold and let it evolve under the Ricci flow. As time goes on, the flow smooths out the geometry, making the curvature more uniform. But as we've discussed, singularities might form. However, thanks to Perelman's surgery techniques, we can keep the flow going and watch how the geometry changes over long periods of time.
So we're essentially letting the shape evolve under the Ricci flow and observing its long-term behavior to deduce its fundamental geometric structure.
Precisely. And Thurston's geometrization conjecture states that eventually the shape will decompose into pieces, each of which has a very specific geometric structure. These pieces can be classified into 8 different types, each corresponding to a different building block of three-dimensional geometry.
Wow, so it's like the Ricci flow acts as a kind of geometric sorting machine, separating a complex shape into its fundamental geometric components.
That's an excellent analogy. And this decomposition into geometric building blocks is what allows us to classify three-dimensional manifolds and understand their topological properties. It's like breaking down a complex molecule into its constituent atoms to understand its chemical behavior.
This is incredible. It's like we've found a way to unlock the secrets of three-dimensional shapes by watching them dance and evolve under the Ricci flow.
Indeed. And this dance is guided by the entropy, the no-breathers theorem, the no-local collapsing theorem, the ancient solutions, and all the other amazing concepts we've discussed.
Professor, this has been an absolutely mind-blowing journey. We've journeyed from the abstract world of entropy to the concrete world of geometric surgery and the grand vision of Thurston's geometrization conjecture. I'm starting to appreciate the depth and beauty of Perelman's work.
It is truly beautiful and profound work, and we've only scratched the surface. There's still so much more to explore in the world of Ricci flow and its applications.
Well, Professor, I'm eager to continue our exploration. In the next and final part of our deep dive, can we delve into the details of this thick-thin decomposition and how it helps us classify three manifolds? I'm particularly curious about those 8 geometric building blocks you mentioned.
Absolutely. We'll explore how Perelman's work allows us to identify those thick and thin regions and how this dichotomy leads to a complete understanding of three-dimensional topology. It's like assembling a puzzle where the Ricci flow provides the pieces and Thurston's geometrization conjecture gives us the picture on the box.
I can't wait. Until next time, keep those brain gears turning. The world of mathematics is full of fascinating discoveries just waiting to be explored. Welcome back to our deep dive into the incredible world of Perelman's work on the Ricci flow. In the previous parts, we've covered a lot of ground. Entropy, no breathers, no collapsing, L-geometry, ancient solutions, even geometric surgery. Now in this final part, I'm excited to see how all these pieces come together to reveal a stunning picture of three-dimensional spaces.
It is quite remarkable how these seemingly disparate concepts weave together to form a cohesive and powerful theory. It's like watching a tapestry being woven thread by thread until a breathtaking image emerges.
Exactly. And in the last part, you left us on a cliffhanger talking about Thurston's geometrization conjecture and this idea of a thick-thin decomposition. Can you unpack those ideas for us?
Absolutely. Thurston's geometrization conjecture is a grand vision for classifying all three-dimensional manifolds. It proposes that any three-manifold can be broken down into pieces, each of which has a specific geometric structure. Think of it like a periodic table for three-dimensional shapes, where each element represents a fundamental building block of geometry.
Oh, okay. That's starting to make sense.
Yeah.
But how do we actually break down these shapes into their fundamental components? You mentioned something about a thick, thin decomposition. What does that mean?
Imagine you have a long, thin tube. If you zoom in on a small section, it might look almost flat like a piece of paper. But if you zoom out and look at the tube as a whole, you can clearly see its curvature. That's the essence of the thick-thin decomposition.
I see. So the thin parts are the regions where the curvature is highly concentrated, and the thick parts are the regions where the curvature is more spread out and gentle.
Precisely. And Perelman showed that for a three-manifold evolving under the Ricci flow, we can pinpoint these thick and thin parts with remarkable precision.
So the Ricci flow is like a sculptor shaping the manifold over time, pushing the curvature into these concentrated thin regions and smoothing out the thick regions.
That's a beautiful way to put it. And as the Ricci flow continues to sculpt the manifold, it reveals this remarkable decomposition.
Okay, I'm on the edge of my seat. Tell me, what does this decomposition look like? What are these fundamental geometric building blocks you mentioned?
Well, Perelman's work shows that if we let a closed three-manifold evolve under the Ricci flow for a long enough time, it will decompose into two main types of pieces. One, hyperbolic pieces. These are the thick parts of the manifold. They have a very specific geometric structure resembling hyperbolic space, which is a space of constant negative curvature. Imagine a saddle shape. That's a classic example of a surface with negative curvature.
Okay.
And two, graph manifold pieces. These are the thin parts of the manifold. They're formed by gluing together simpler pieces like solid tori along their boundaries. Solid tori is essentially donut shapes, and graph manifolds are built by assembling these donuts in a specific way.
So we have these negatively curved hyperbolic pieces and these donut assemblies called graph manifolds. And the Ricci flow tells us how to break down any three-manifold into these fundamental components.
Exactly. And this decomposition is incredibly powerful because it allows us to classify three manifolds and understand their topological properties. It's like having a blueprint for three-dimensional space itself.
This is mind-blowing. So if I give you any three-dimensional shape, you can use the Ricci flow to tell me what kind of hyperbolic pieces and graph manifold pieces it's made of.
In theory, yes. Although in practice, carrying out the decomposition can be incredibly complex. But the point is that Perelman's work gives us a roadmap, a way to understand the underlying structure of any three-dimensional shape.
It's like we found the Rosetta Stone for three-dimensional geometry.
That's a great analogy, and just as the Rosetta Stone allowed us to decipher ancient Egyptian hieroglyphs, Perelman's work is helping us decipher the language of three-dimensional space.
This is incredible. So by identifying the hyperbolic and graph manifold components of a shape, we can unlock its deepest secrets.
Precisely. For example, we can determine whether the manifold is simply connected, meaning any loop on the manifold can be continuously shrunk to a point.
So just by knowing the geometric decomposition, we can infer fundamental topological properties. That's remarkable.
It is, and this is just the tip of the iceberg. Perelman's work has opened up entirely new avenues of research in geometry and topology. Mathematicians are still exploring the full implications of his groundbreaking results.
Professor, this has been an incredible journey. We've delved into the depths of Perelman's work, from the entropy formula to the no-local collapsing theorem, L-geometry, ancient solutions, geometric surgery, and finally, this amazing thick-thin decomposition. I'm truly in awe of the power and beauty of mathematics.
It is a testament to the power of human curiosity and the elegance of mathematical reasoning. And the best part is that there's still so much more to discover in the vast and ever-expanding universe of mathematics.
Well said. Who knows what other hidden patterns and profound connections are waiting to be uncovered? Maybe one day our deep dive will explore those uncharted territories.
I certainly hope so. It's these kinds of explorations that remind us of the boundless wonders of the mathematical world.
Indeed. Until then, keep those brain gears turning. The world of mathematics is full of fascinating discoveries just waiting to be explored. All right, let's jump right into a deep dive today, into some fascinating math.
Sounds good.
We're going to be looking at Grisha Perelman's paper, the entropy formula for the Ricci flow, and its geometric applications.
Oh yeah, a classic, a dense one, but truly groundbreaking stuff.
It is. And you know what's crazy is this paper was originally published back in 2002. But here we are in 2025 with this updated version, and it's still like causing a stir.
Oh, absolutely. Perelman's work on the Ricci flow, I mean, it's completely reshaped how we think about geometry and topology.
Okay, so for our deep dive today, we're going to really zero in on the proof of the entropy formula and what it all means.
Okay.
And one of the biggest things there is this concept of no breathers.
Right.
Meaning no periodic orbits in the Ricci flow.
Huge breakthrough, basically saying no metrics can, evolve under the Ricci flow and then cycle back to their original shape.
Except for
the very specific case of a gradient Ricci soliton.
Right. Yeah. Okay, so let's rewind a bit, for folks who might not be totally familiar.
Okay.
Can you give us a quick refresher on what the Ricci flow is at its core?
Sure. So at its heart, the Ricci flow, it's an evolution equation.
Okay.
It's for a Riemannian metric. And what it does is it describes how a space's geometry changes over, quote, time, driven by its curvature.
So are we talking like watching a surface kind of deform, smoothing out its bumps and wrinkles as time goes by?
Yeah, that's a good visual starting point, but we got to remember that this smoothing out idea, it's not just a visual analogy, it's deeply embedded in the math itself.
Right.
The Ricci flow equation, it precisely describes how the metric, which determines distances and angles, changes based on the curvature at each point.
And this equation, this was first introduced by Richard Hamilton, right?
That's right. Yeah, he used it to prove some pretty impressive convergence results for manifolds with special curvature conditions.
Right. He laid the groundwork, and then Perelman came along and just took it to a whole new level.
Absolutely.
Yeah. All right, so back to Perelman's paper. He starts off by highlighting how the Ricci flow can actually be thought of as a gradient flow. Can you unpack that for us? What does that actually mean in this context?
Sure. So a gradient flow, it describes how a system will, evolve to minimize some kind of energy, like imagine a ball rolling down a hill.
Okay.
Naturally, it'll seek out the lowest point where its potential energy is minimized, right?
Makes sense.
So in the case of Ricci flow, the energy we're talking about, it's tied to this functional that Perelman defines, denoted by F.
And this functional, it sort of captures like certain geometric properties of the space, right?
That's exactly it. It measures how non-uniform the curvature is.
Okay.
So a high value of F means the curvature is all over the place, like that crumpled paper you were talking about earlier. And a low value suggests a smoother, more uniform geometry.
So basically, the Ricci flow, as a gradient flow, it's trying to like minimize this F, essentially ironing out those wrinkles in the geometry.
That's the core idea, yeah.
Okay, I think I'm following so far.
Perelman actually proves that the Ricci flow can be interpreted as a gradient flow for a slightly modified version of this functional,
Gotcha.
which he denotes by Fm, and this one is defined with respect to a fixed measure on the manifold.
Okay, so what's the significance of this fixed measure then?
You can think of it as a way of assigning different weights to different parts of the space. When you're calculating the functional, it's kind of like saying some wrinkles on our paper are more important to smooth out than others,
So changing the measure is like shifting our focus on which wrinkles matter most.
Yeah.
But the actual ironing process, the Ricci flow itself, that stays essentially the same.
Precisely.
Gotcha.
The key point is the choice of this measure doesn't affect the resulting flow up to a diffeomorphism.
Ah, yes, diffeomorphisms, those smooth invertible transformations. So it's like stretching or bending our crumpled paper without tearing it.
Exactly.
Or poking any new holes in it.
The flow itself is invariant under these transformations.
Right.
Yeah.
Now, I remember that Perelman connects this whole gradient flow perspective to some pretty heavy-duty concepts from physics, specifically the Bochner-Luknerovich formulas.
Yeah.
Can you refresh our memory on those? What are they all about?
Okay, so these formulas, they're fundamental in differential geometry, and they relate the curvature of a manifold to certain differential operators, acting on things like vector fields and spinors.
So they're providing a bridge between, like, the geometric properties of a space and the tools of calculus and analysis.
Exactly.
Okay.
And what Perelman does is he shows that when you modify these formulas to incorporate that fixed measure from our M at M functional, we get expressions that involve the Bakry-Emery-Ricci tensor.
Wow. Okay, that's a mouthful.
It is.
So what's so special about this particular tensor in this context?
Well, it's key because it pops up in those modified Bochner-Luknerovich formulas.
Okay.
And it's closely tied to the Ricci flow itself. So by making this connection, Perelman's really setting the stage for some profound insights into how the flow behaves.
So essentially, he's weaving together these different ideas from geometry, analysis, and physics.
Yeah.
To build this powerful framework for studying the Ricci flow.
Exactly.
And this is just the beginning.
It is, yeah.
Okay, so from here, he goes on to prove this remarkable result about the Ricci flow, which he calls the no-breathers theorem.
Right.
This is where things start to get really interesting.
Yeah.
So remind us, what are breathers in this context, and why do they matter?
So in the world of Ricci flow, a breather, it's a metric that essentially cycles back to its original shape.
Gotcha.
After some time, maybe with a scaling factor thrown in.
So like watching our crumpled paper magically uncrumple itself and then just crumple back into the same shape over and over.
Exactly. A periodic solution to the Ricci flow equation.
Yeah.
And Perelman proves that, except for the special type of solution called a gradient Ricci soliton, there are no non-trivial breathers.
So if our paper is doing this uncrumpling and recrumpling loop, it's got to be a very special kind of crumpling governed by this gradient Ricci-Soliton solution.
That's right.
Interesting.
Yeah, and to prove this, he introduces a modified version of the f functional, which he calls w.
Okay.
And this w functional depends not only on the metric in a function, but also on a scale parameter,
Okay.
which is denoted by tau.
Ah, tau. Our zoom in, zoom out parameter lets us analyze the behavior at different levels of detail.
Exactly. And here's where Perelman's ingenuity really shines through.
Got it.
He shows that this W functional, it has this remarkable property.
Mm.
It's monotonically decreasing under the Ricci flow.
Meaning it can only go down or stay the same
Precisely.
as the flow progresses.
Yeah, and the seemingly simple property, it has huge implications.
Yeah.
If we had a breather, a metric that cycles back to its original shape,
Right.
then the W functional would have to return to its original value after each cycle, right?
Right, because it's back where it started.
But if it can only decrease or stay the same.
And it can't happen. It'd be like a ball rolling down a hill, suddenly jumping back up.
Exactly. The monotonicity of W acts as a constraint, effectively ruling out those non-trivial breathers.
Wow. So he's using this clever mathematical trick to just eliminate an entire class of solutions to the Ricci flow.
And this no-breathers theorem, this is just the beginning, it sets the stage for even deeper insights into the nature of the flow and its long-term behavior.
Okay, we've covered gradient flow perspective, connections to the Bochner-Lichnerowitz formulas, and now this amazing no-breathers theorem.
Yep.
What's next in Perelman's journey?
Well, from here, he introduces this really crucial concept, the idea of reduced volume.
Right.
It's a bit more abstract.
Okay.
But it gives us a powerful new lens for understanding the Ricci flow, especially how those singularities form.
Okay. I'm intrigued. Tell me more about this reduced volume.
All right. To really grasp it, we need to shift our perspective a bit. Imagine our crumpled piece of paper, but now it's embedded in a much larger, higher dimensional space.
Okay, I'm trying to picture that.
Think of the Ricci flow happening on our three-dimensional paper as like a shadow of a process happening up in this higher dimensional space.
So the Ricci flow is like a projection of something more complex.
Exactly.
Happening in some unseen realm.
A good way to think about it.
Okay.
Now, the reduced volume, it's a way of measuring the size of this shadow in a meaningful way.
So it's giving us information about this higher dimensional context, even though we're focused on the three-dimensional flow.
Exactly.
Okay.
And the truly remarkable thing is that this reduced volume, it also exhibits monotonicity under the Ricci flow.
Hold on. It can only decrease or stay the same, never increase.
That's right.
It's like the W functional all over again.
You got it.
Oh.
They're both providing different but complementary perspectives on the same underlying phenomenon.
Okay.
The way that the Ricci flow smooths out the geometry and drives it towards these equilibrium states.
So the reduced volume, like WU, it's another tool for controlling the flow's behavior.
Yes.
And understanding its long-term evolution.
Precisely.
This is really amazing. It's like Perelman's found a way to, like, navigate this treacherous terrain of singularities without getting totally lost in the chaos.
It really is. It's a testament to his deep understanding of the Ricci flow and how to build these powerful tools for analyzing it.
Okay, so we've got this reduced volume thing. It's monotonically decreasing. Helps us rule out certain types of singularities.
Yeah.
Where does Perelman take us from here?
Well, he goes on to explore these connections between the Ricci flow and, get this, thermodynamics.
Thermodynamics, like heat and entropy and all that.
That's right.
How does that even relate to geometry?
It's surprising, but it's incredibly fruitful.
Okay.
He draws this analogy between the Ricci flow and how heat diffuses.
So is he saying that the Ricci flow is like heat spreading out on a surface, smoothing out those temperature differences?
That's the basic idea, yeah. And in thermodynamics, we've got this concept of entropy, which, roughly speaking, measures the disorder or randomness of a system.
Right, and Perelman's suggesting there's some geometric version of entropy within the Ricci flow.
He proposes that the W functional, remember that one?
Yeah.
It can be thought of as a kind of geometric entropy.
So a manifold with like really messed up curvature, like our super crumpled paper, that would have high geometric entropy.
Yes, and as the Ricci flow smooths out the geometry, that geometric entropy decreases, just like entropy tends to increase in a closed physical system.
So there's like a thermodynamic arrow of time in the Ricci flow, driving it towards these lower entropy states.
Beautiful way to put it, yes.
This is incredible. We've gone from crumpled paper to higher dimensional spaces.
I know, right?
And now we're connecting geometry to the fundamental laws of physics.
It's all connected.
It is. It really is.
It's a testament to how interconnected different areas of math and science are. And Perelman's work is a perfect example of how exploring those connections can lead to these massive breakthroughs.
All right, my mind is officially blown.
Mine too.
We've covered so much ground already, but I know there's still more to come.
There is.
What's next on our Perelman adventure?
Well, next we're diving into the heart of his work, his proof of the Poincaré conjecture, a problem that had stumped mathematicians for over a century.
This is what I've been waiting for, the Poincaré conjecture.
Right.
It always seems so abstract and out of reach, but now we're going to see how Perelman cracked it using all the tools we've been talking about.
It's truly remarkable.
It is. It is. I can't wait.
We'll explore it in detail in part 2. Welcome back. Ready to dive deeper into Perelman's work?
Oh, absolutely. I'm still trying to wrap my head around this reduced volume thing.
Yeah, it's a tricky one.
And how it all ties into those singularities.
It's a powerful concept, you see. The Ricci flow, the way we usually picture it, it operates on a three-dimensional manifold. But Perelman's insight was that we can gain a deeper understanding, by thinking of this manifold as embedded in a much larger space, potentially even infinite dimensional.
So we're like zooming out, getting a broader perspective on the whole thing.
Exactly. And in this larger space, the Ricci flow takes on a more nuanced form.
All right.
It's not just about smoothing wrinkles on a surface anymore. It's about how the whole manifold evolves within this bigger context.
All right. I'm starting to see why this approach is so powerful. But how do we actually work with this higher dimensional space? It seems so abstract.
That's where reduced volume comes in. It's a mathematical tool that lets us quantify how the manifold is changing within this larger space.
So it's giving us a way to actually measure something that would otherwise be too slippery to grasp.
Precisely. It takes into account not only the intrinsic geometry of the manifold, the distances and angles and curvature, but also its extrinsic geometry, how it sits within the larger space.
And you mentioned earlier that reduced volume has this monotonicity property under the Ricci flow.
Yes, that's one of Perelman's key insights.
It can increase, only decrease, or stay the same.
Right. And this has major implications for understanding how those singularities form.
Okay, let's talk about singularities.
Yeah, okay.
They've been kind of lurking in the background of our conversation.
Yeah, they're important.
Can you remind us what they are and why they're so crucial to all of this?
So singularities, they're points in space-time where the curvature becomes infinite. They're the spots where the Ricci flow, as we traditionally understand it, breaks down.
Like our crumpled paper developing an infinitely sharp point.
That's a good analogy.
Okay.
And understanding how they form is crucial for figuring out the long-term behavior of the Ricci flow.
Gotcha.
They're like the trouble spots where things can get unpredictable.
So is Perelman using the reduced volume to, like, tame these singularities?
You could say that the fact that reduced volume is monotonic, it puts a limit on how singularities can form.
Interesting.
Prevents certain types of bad behavior.
Can you give us an example of what you mean by bad behavior?
Sure. One type that Perelman rules out is called local collapsing.
Okay.
Imagine a region of our manifold shrinking down to a point while the curvature there blows up to infinity.
Like a tiny wrinkle becoming infinitely sharp and dense.
Exactly. And Perelman's no local collapsing theorem, which he proves using reduced volume, says that this can't happen under the Ricci flow.
So the reduced volume is like a safety net, keeping the geometry from going completely haywire as it evolves.
I like that analogy. The monotonicity of reduced volume provides a kind of global control over the flow, making sure that even when singularities do form, they do so in a predictable way.
This is mind-blowing. It's like Perelman's found a way to navigate this minefield of singularities and come out unscathed.
It really is a testament to his understanding of the Ricci flow and his ability to develop these powerful tools.
Well, we've got this incredible reduced volume. It's monotonic. Helps us rule out certain types of singularities.
Yeah.
Where does Perelman take us next?
Well, buckle up, because he goes on to connect the Ricci flow with something you might not expect. Thermodynamics.
Thermodynamics.
Yeah.
Like heat and entropy and all that.
You got it.
I'm having trouble picturing how that relates to geometry.
It's a surprising connection, but it turns out to be incredibly fruitful.
Okay.
He makes this analogy between the Ricci flow and the way heat spreads out.
So is he saying the Ricci flow is like heat diffusing on a surface, smoothing out temperature differences over time?
That's the basic idea.
Okay.
And in thermodynamics, there's this concept called entropy, which basically measures how disordered or random a system is.
Right.
Perelman suggests there's a geometric counterpart to entropy.
Okay, so within the Ricci flow.
Exactly. He proposes that the W functional, remember that from earlier?
Oh, yeah.
Can be interpreted as a kind of geometric entropy.
So a manifold with really wild curvature, like our super crumpled paper, would have high geometric entropy.
That's right. And as the Ricci flow smooths out the geometry, this geometric entropy decreases, just like entropy tends to increase in a closed physical system.
So there's like a thermodynamic arrow of time in the Ricci flow, driving it towards these states of lower geometric entropy.
That's a beautiful way to put it.
Wow, we've come a long way from crumpled paper.
We have.
Higher dimensional spaces, and now we're linking geometry to the fundamental laws of physics.
It's a testament to the interconnectedness of math and science.
Yeah.
And Perelman's work is a prime example of how exploring those connections can lead to these huge breakthroughs.
My mind is officially reeling. This has been such a mind-bending journey.
It's pretty amazing.
But I know there's still more to come.
Oh yes, the best is yet to come.
What's next on our Perelman adventure?
Next, we're going to tackle the heart of it all, Perelman's proof of the Poincaré conjecture.
This is it, the Poincaré conjecture.
The one and only.
A problem that stumped mathematicians for over a century. And now we're going to see how Perelman cracked it.
Using all the tools we've been talking about.
I can't wait.
It's a remarkable achievement, and we'll explore it in detail in the next part.
Bring it on. Okay, we're back, ready for the grand finale.
The big one.
Perelman's proof of the Poincaré conjecture.
Here we go.
It's amazing, right, how we started with this basic idea of the Ricci flow. And now we're here, these powerful concepts like reduced volume, geometric entropy.
Yeah.
And it all comes together to solve this century-old problem.
It really shows you the power of math, you know?
It does.
Perelman's work, it didn't just solve the conjecture, it opened up all these new paths for research in geometry and topology.
So before we get into the nitty-gritty,
Okay.
can you remind us of what the Poincaré conjecture actually says? I always get a little tripped up on the details.
It can be a bit tricky.
It's something about 3D shapes and spheres, loops that can shrink to a point.
Right. So basically, the Poincaré conjecture, it states that if you've got a three-dimensional space that's simply connected, meaning any loop you draw on it can be shrunk down to a point without leaving the space, then that space has got to be topologically equivalent to a three-dimensional sphere.
All right, so let me make sure I'm following. Simply connected means no holes or handles, anything that'd stop a loop from shrinking.
Exactly.
And topologically equivalent means we can stretch and bend the space without tearing it or making holes, and it'll end up looking like a sphere.
That's it. The conjecture says those two properties, being simply connected and being topologically a sphere, they're the same thing for 3D spaces.
Sounds simple enough when you put it like that.
Yeah, but proving it, that was the tough part.
That's where Perelman comes in.
Exactly.
The Ricci flow.
His big idea was that the Ricci flow could be used to, simplify the topology of these three-dimensional spaces, gradually untangling a knot.
So the Ricci flow can transform a complicated shape into something simpler, hopefully a sphere.
Yeah, but there are roadblocks along the way.
Like what?
Remember those singularities we talked about?
Oh, right. The points where curvature goes wild.
Those can really mess things up, get in the way of the smooth flow.
Like hitting a snag while you're untangling that knot.
Perfect analogy.
Okay.
So to deal with this, Perelman developed a technique called Ricci flow with surgery.
Ricci flow with surgery. That sounds intense.
It is. It's a very precise process.
Okay.
When the flow gets close to a singularity, Perelman carefully cuts out a small region around it.
Okay.
Replaces it with a smooth cap, basically removes the problem and lets the flow continue.
So he's modifying the geometry to get around those singularities.
Exactly. And the brilliance is that by doing these surgeries strategically, he can guide the Ricci flow to simplify the topology without getting stuck.
But he's outsmarting those singularities, keeping the flow moving towards its goal.
And what he showed is that by using this Ricci flow with surgery technique over and over, any simply connected three-dimensional space can eventually be turned into a bunch of pieces that are either spheres or what he called extinction caps.
Extinction caps, what are those?
They're these special pieces of geometry that basically disappear under the Ricci flow.
Okay.
Collapse down to nothing.
So you're left with just a bunch of spheres.
Exactly. And because we started with a simply connected space, these spheres have to be connected in a specific way.
To form one big sphere?
Precisely.
So Perelman showed that by using the Ricci flow, smoothing out the geometry, strategically performing these surgeries, any simply connected 3D space will ultimately turn out to be topologically a sphere.
That's the essence of his proof of the Poincaré conjecture.
It's incredible. We started with this concept of curvature, and we ended up with the solution to one of the biggest problems in math.
It's a journey that shows how connected all these different areas of math really are.
It really does.
Differential geometry, topology, even physics.
Yeah.
Perelman's work is a testament to what human curiosity and the pursuit of knowledge can achieve.
I gotta admit, I'm feeling a bit overwhelmed. But in a good way, this has been such a mind-expanding deep dive.
I know, right? It's inspiring to see how something as abstract as the Ricci flow can lead to such profound results.
Absolutely. Thank you so much for guiding us through this.
My pleasure.
It's been truly enlightening.
And to all our listeners out there, keep exploring the world of math. There's always something new to discover, new connections to make.
Until next time, stay curious, everyone. Welcome back, everyone, to another deep dive. Today, we're taking a look at, it's a pretty famous paper in the world of mathematics.
Oh, yes.
It's Grisha Perelman's The Entropy Formula for the Ricci Flow and its Geometric Applications.
Groundbreaking work.
It is, and, it's known for its connection to solving the Poincaré conjecture, which was...
Huge problem in topology.
Yeah, really a big one. And at the center of it all is this idea of the Ricci flow. Now, we're lucky to have an expert with us today.
Happy to be here.
So I think a lot of our listeners are familiar with the Poincaré conjecture, but the Ricci flow might be a little bit more of a mystery. Could you maybe give us a way to visualize what it's all about?
Absolutely. Imagine you have a crumpled piece of paper.
Okay, got it.
Now, the Ricci flow, think of it as a way to smooth out those wrinkles and bumps on the paper over time.
Okay, like you're literally just making the paper flat again.
In a way, yes. Mathematically, it's described by this equation. d dt, g sub e sub, equals 2 roc sub e sub. Here, g sub e sub, that represents the metric of the space. It tells us how we can measure distances.
Right.
And our sub e sub, this represents the Ricci curvature, so that gives us a way to measure how much our space is bent.
Okay, so the equation shows how the metric, the way we measure distances, changes over time.
Exactly. And it changes in a way that makes the curvature smaller, leading to a smoother space.
So if we take this idea of the Ricci flow smoothing out the curvature, does that always mean everything ends up as a sphere? Because a sphere, in 3D, it's the smoothest thing, right?
That's a great question, and it brings up a really important point. The Ricci flow, it does smooth things out, but the final shape, well, it depends on what you start with. The initial shape and the topology of the space.
Well,
think of it like you can smooth out a donut, to make it perfectly round.
Sure.
But you're always going to have that hole in the middle.
Right. It's still a donut.
Exactly. The topology, the basic shape, it stays the same.
Okay, that makes sense. Now, Perelman's paper goes into some really deep aspects of the Ricci flow. And one of the things he talks about is breathers. What are those and why are they important here?
A breather. Imagine a shape that could, in theory, keep coming back to its original form after going through the Ricci flow.
Like, it changes, but then it always goes back to how it started.
Exactly. Imagine a rubber band stretching and contracting over and over. A breather would be a shape that does something similar with the Ricci flow.
It's like the shape is breathing in and out as it evolves.
Precisely. Now, one of the big things Perelman did was prove that, except for a special case, these breathers, they don't exist.
So things don't just keep cycling back to how they started.
Right. Shapes generally just keep evolving.
Now, how did he actually prove that? I mean, I'm guessing the math behind it is pretty complex.
Oh, it is. One of the tools Perelman used is called the logarithmic Sobolev inequality. It's a result that comes from probability theory.
Probability. So we're bringing in ideas from a totally different area of math.
That's right. He used it to show that the energy of a shape, measured by a specific mathematical function, always decreases under the Ricci flow.
Okay, so this energy keeps going down, and that prevents the shape from coming back to its original form.
You got it. It's like a one-way street.
Now, you said energy of a shape. What exactly is this function that Perelman uses to measure that energy?
It's given by this expression, F A's sub R plus S phi-sub. So R represents the scalar curvature.
Right, we talked about that. It measures how curved the space is.
Exactly. R represents the gradient of a function F. Think of it like the steepness of a slope at each point in our space.
Okay, and dv is just a tiny bit of volume.
That's right. So this whole function, it basically captures how the curvature and the steepness contribute to the overall energy.
And what about that f? What does that function represent?
Ah, that's important. F is the function we're trying to find, the one that makes this energy as small as possible.
Like finding the lowest point in a landscape.
Exactly. It's called the minimizer. And if we know it, it tells us a lot about how the shape changes under the Ricci flow.
So finding f is like solving a key part of the puzzle.
Exactly. And Perelman's work gives us a way to find this minimizer.
That's amazing. You mentioned earlier that there's a special case where breathers do exist. What is it?
Ah, yes. They're called gradient shrinking solitons. Think of a balloon deflating perfectly symmetrically.
Okay.
It shrinks, but the shape stays the same. Gradient shrinking solitons are like that. They evolve under the Ricci flow, but their basic geometric features remain the same.
So they're like self-similar solutions to the Ricci flow.
Exactly. Shrinking, but keeping their form.
Fascinating.
Now, there's another key concept in Perelman's paper in section 4. It's the no-local collapsing theorem. This looks at what happens when parts of a shape start to shrink really fast under the Ricci flow.
Like imagine our crumpled paper tearing as we try to smooth it out.
Yeah, that's a good way to picture it. Collapsing means those regions shrink so much they might actually disappear. But this theorem says that under certain conditions, that can't happen.
What conditions?
The theorem says that if we only look at the flow for a limited time, then the shape won't completely collapse.
So you're saying it might get really thin, but it won't vanish entirely.
Exactly. The theorem also uses the term local, which means it applies even if some parts are super curved. It's saying the flow is controlled even when things get a bit wild.
Okay, I think I'm starting to get it. It's a bit like squeezing a balloon. You can make parts of it thin, but it won't pop as long as you don't squeeze forever.
A perfect analogy. And to prove this, Perelman introduces something called non-collapsing.
Okay, and what is that?
Think of it like a measure of thickness. It tells us the minimum volume a shape can have as it evolves, even in areas of high curvature. It's like saying, no matter how much you squeeze the balloon, it can't get thinner than a certain limit.
So it's like a built-in safety mechanism.
Yeah, exactly. To prove this, Perelman uses another amazing tool, a monotonicity formula that he created.
And what does that do?
It acts like a safeguard, stopping the volume of the shape from shrinking too fast. It ensures the volume doesn't go below a certain point, even when the curvature is high.
Like a mathematical safety net.
Precisely. Now, we've gone over some key concepts, but Perelman's paper goes much deeper. He proves everything rigorously, demonstrating the power of mathematical reasoning.
And that leads us to section 5, where Perelman focuses on proof. For our listeners who might not be familiar with how important proofs are in math, can you explain that a bit?
Sure. Proofs are what make mathematics certain. They're not just about checking if something works. They tell us why it's true.
Right. It's like building a house on a solid foundation.
Exactly. And in Perelman's paper, the proofs aren't just boring calculations. They're filled with clever arguments and unexpected connections, like we saw with the logarithmic Sobolev inequality.
He really brings together different areas of math.
He does. He blends geometric intuition with powerful analytical tools, which makes his work so groundbreaking.
It's really inspiring to see. Maybe before we go on, we could quickly recap the main points so far.
Of course. Let's see. First, we have the Ricci flow itself. It's like smoothing out wrinkles in a space, always trying to reduce curvature. Then there are the breathers, those hypothetical shapes that cycle back to their original form. Perelman proved, except for a special case, that they don't exist. So under the Ricci flow, shapes keep evolving. And then there's the no local collapsing theorem, which tells us that parts of a shape won't just vanish under the Ricci flow under specific conditions. And of course, Perelman uses amazing tools like the logarithmic Sobolev inequality and the monotonicity formula to prove all this.
Wow, that's a lot to digest. But I think we're ready for the next stage of this journey. Let's dive deeper.
Sounds good. So in section 6, Perelman, he takes this really interesting approach. He embeds our system, the one we've been talking about, into a larger, like a standard system, using something called Riemannian geometry.
Okay, hold on. Embedding systems. We were just talking about smoothing out paper. Now we're embedding things.
Yeah.
Can you connect those ideas for me?
Sure. Remember, we're trying to understand this Ricci flow, right? And sometimes you need to look at things from a different angle, a different perspective. So what Perelman does is he constructs this higher dimensional manifold. He calls it men. And it's
Right.
basically our original manifold, M times a high dimensional sphere, sup and sup, and then times the positive real line. It's like, oh, well, you're adding these extra dimensions.
Okay. I'm trying to picture this. What does this higher dimensional space tell us about the Ricci flow?
Okay, imagine like a little 2D creature living on the surface of a balloon. It
Yeah.
only understands 2D geometry, right? But we can see the whole balloon in 3D.
Hmm.
So this M, it's kind of like that. It lets us look down on our 3D manifold M from a higher dimension. It gives us more information.
Ah, okay. So this higher dimensional space, it's like a vantage point.
Exactly. Now, the metric on this M, it involves our evolving metric G sub adject on M, and also a standard metric G sub I sub on the sphere. But the key part is the sub-zero subcomponent. It's got the scalar curvature R of our evolving metric, and the scaling factor N, which is the dimension of the sphere. And this Gris sub-zero sub, it's closely related to something called Hamilton's matrix Harnack expression.
Okay. That sounds familiar. That's important for understanding how the Ricci flow changes, right?
Exactly.
So it seems like this metric isn't just random. It's very specific. Like it's designed to show us something about the Ricci flow.
You got it. Perelman shows that the components of the curvature tensor of this metric on M, well, they basically match up with the components of the matrix Harnack expression, except for a factor of n sup 1 sup. And even more, all the components of the Ricci tensor on this higher dimensional space, they're 0, again, modulo n sup 1 sup.
Okay, I think I'm getting lost here. What does it mean that the Ricci tensor is essentially 0 in this higher dimensional space? Why is that important?
Well, when the Ricci tensor is practically 0, it means this space with this special metric, it's almost Ricci flat.
Okay.
And Ricci flat spaces, they're very special in Riemannian geometry. They have a lot of really nice properties. The n sup 1 sup factor, that just tells us these properties hold approximately, and they get more accurate as the dimension of the sphere. That n gets bigger.
So Perelman he's using these special properties of Ricci flat spaces to help him understand the Ricci flow. It's like he's using a really powerful magnifying glass.
Yeah.
But how does this connect to the heat equation and the conjugate heat equation? We talked about those before.
Great question. Perelman shows that these equations on our original manifold, M, well, you can interpret them through the Laplace equation on this bigger space, M. And the Laplace equation, it's really fundamental. It describes how things spread, like diffusion.
So we're seeing heat flowing on our manifold, and it's like it's actually diffusion happening in this bigger space. It's like watching a ripple spread on a pond, but the pond is actually multidimensional.
That's a great way to put it. It shows how Perelman is connecting these seemingly different ideas from math.
Now we have this higher dimensional space as a pay with this special metric. What does Perelman actually do with it? How does he use it to analyze the Ricci flow?
He uses transformations, very specific ones, to change the metric. It's like he's molding it into a shape that's easier to work with. First, he uses the diffeomorphism. It's like a smooth deformation of the space. And this diffeomorphism depends on that minimizer function at f that we talked about earlier.
Right, the one that minimizes the energy.
Yeah, exactly. And this leads to a new metric, and this new metric reflects the properties of something called the backward M-preserving Ricci flow.
Can you remind me what that is again?
Yeah.
The backward impreserving Ricci flow?
Sure, it's like the regular Ricci flow, but we're going back in time and we're keeping a certain measure constant.
Okay, so by changing the metric on this higher dimensional space, Perelman is encoding information about this backward flow.
Precisely. This new metric gives him a new way to look at the Ricci flow, a new perspective that might reveal things that were hidden before.
So what kind of new information does this give him?
Well, this new perspective allows him to connect something called entropy to the Ricci flow.
Entropy, like a measure of disorder.
Yes, exactly. He shows that the entropy multiplied by the inverse temperature is basically minus the total scalar curvature of a particular hypersurface in this transformed higher dimensional space.
Okay, now we're talking about entropy, temperature, and hypersurfaces. Can you help me understand how those all fit together?
Imagine you take a slice of min at a fixed value of the scaling parameter.
Okay.
That slice, that's a hypersurface. It's a space with one less dimension. And the total scalar curvature of this hypersurface, it's directly related to the entropy of our system.
So the curvature of this slice tells us something about the entropy of the Ricci flow.
That's pretty wild.
It is. It shows how powerful geometric thinking can be. By building and studying these geometric objects, we can understand concepts that seem completely different. That's something you see a lot in Perelman's work.
Okay, I think I'm starting to see the connections here. But there's one thing I'm still not quite getting, the Bishop-Gromov relative volume comparison theorem. Can you explain that in a simple way? And how does Perelman use it?
Sure. The Bishop-Gromov theorem, it's a tool in Riemannian geometry, and it helps us compare volumes of balls in different spaces. Basically, it says that if a space has non-negative Ricci curvature, then a ball of a certain radius can't be much smaller than a ball of the same radius in, say, Euclidean space.
So spaces with non-negative Ricci curvature, they can't be thinner than Euclidean space.
Exactly. And this is really important for Perelman's work. He uses it to show that something called the reduced volume, it always decreases along the Ricci flow. And this decreasing property is super important for understanding how the flow behaves in the long run and for proving the Poincaré conjecture.
Wow, we've gone pretty deep into the math here. I'm starting to appreciate how complex and interconnected these ideas are.
Yes, definitely. Perelman's work is a beautiful blend of geometry, analysis, and topology. It's this combination that makes his work so groundbreaking.
Before we move on, are there any other key takeaways from this section that our listeners should remember?
Absolutely. I think the main thing to remember from section 6 is this idea of the higher dimensional space and its very special metric. This might seem abstract, but it's a really powerful tool for studying the Ricci flow. It connects it to things like entropy and the Bishop-Gromov volume comparison theorem.
Okay, that helps to solidify things a bit. I'm ready to see what Perelman does next.
Okay, so let's move on to section 7. Perelman introduces a really fascinating way to look at the Ricci flow here. He brings in some ideas from something called comparison geometry.
It's comparison geometry. Okay, I'm curious. What's that all about?
Well, it's basically, you're trying to understand geometric spaces, but you do it by comparing them to spaces that are, well, more familiar, like Euclidean space or hyperbolic space. Think of it like you're trying to understand the shape of a mountain.
Okay.
You might compare it to, say, a cone or a sphere.
Right, so you're using these basic shapes as, like, benchmarks.
Exactly. So what Perelman does is he introduces this idea of L length. It's like, it's a different way to measure how long a curve is, but in a space where the metric is changing because of the Ricci flow.
Okay, so how is it different from regular length?
Well, the L length, it takes into account not just the distance the curve travels, but also the curvature it encounters along the way.
Ah, I see. So it's like if you're hiking, it's not just about how far you walked, but also how steep the trail was and how many turns there were.
That's a great way to put it. And using this L length, Perelman defines these special paths called L geodesics, which are the paths that make this modified length as small as possible.
Okay, and why are these L geodesics important?
Well, they're kind of like the regular geodesics we use to understand, fixed Riemannian manifolds. But these L geodesics, they help us understand the geometry of spaces where the metric is changing because of the Ricci flow.
Right, right. So how do these L geodesics and this L length actually help Perelman analyze the Ricci flow? What can he do with them?
He can derive these really powerful inequalities that relate the L length of curves to the curvature of the space and the time parameter of the Ricci flow.
Okay, can you give me an example of one of these inequalities?
Sure. One important one is Riesch-Wadella and next to Kurlash plus. So here, L is the L length of a curve, L is its Laplacian, it's a way to measure how spread out the curve is, R is the scalar curvature, N is the dimension of the space, it is the time parameter, and K that captures information about the curvature along the curve.
Yeah, that looks pretty complicated. What does that inequality actually mean, like intuitively?
Well, basically it says that how spread out the L length of a curve is, that Laplacian. It's controlled by the curvature of the space and how much time has passed in the Ricci flow.
So the more curved the space is, the more those curves will spread out.
Yeah, that's a good way to think about it. And this spreading out, it's really important for understanding how the whole shape evolves under the Ricci flow.
Okay, that makes sense. You also mentioned something called reduced volume earlier. What is that exactly, and how does it fit into all of this?
Right. The reduced volume, we write it as E, and it basically measures the effective volume of a space from a certain point at a particular time in the Ricci flow. It's defined using the L length of curves coming out from that point and the time parameter.
Yeah.
And Perelman, he proved something amazing. This reduced volume, it always decreases along the Ricci flow.
Always. It never goes up.
Never. It's called monotonically decreasing. And this property, it's really powerful. It gives us a way to control the flow, to understand how it behaves over long periods of time.
It's like a compass, always pointing us downhill, guiding the Ricci flow to where it's going.
Exactly. That's a great analogy. Okay, I know we're running out of time, so let me just quickly go over the rest of Perelman's paper, just the main points.
Okay, yeah, let's get the big picture.
So in sections 8 and 9, he goes deeper into this no local collapsing idea. He gives different proofs, and he extends it to more general situations. He also connects something called the differential Harnack inequality to the fact that the reduced volume always decreases. And then in sections 10 through 13, he really focuses on three-dimensional manifolds. This is the part that's really important for the Poincaré conjecture. He introduces these things called ancient solutions.
Ancient solutions? Is he going back to the beginning of time or something?
No, not quite. Ancient just means these solutions exist for all past time.
Ah, okay.
And Perelman uses these ancient solutions to develop this, what we could call it a surgical procedure.
A surgery for the Ricci flow.
Well, yeah, kind of. It's like when singularities pop up, he carefully cuts them out and replaces them with smooth caps so the flow can continue smoothly. And by doing this over and over, he shows that the Ricci flow can actually go on forever, eventually breaking the original manifold into simpler pieces.
So he's like a cosmic surgeon reshaping space and time.
Yeah, I like that. And then he analyzes these pieces and he shows that they all belong to a very specific class of shapes that we understand really well. And this is what confirms the Poincaré conjecture.
Wow, what a journey. I know we just scratched the surface, but I feel like I have a much better understanding of the Ricci flow now. It's so powerful, and it's amazing how it helps us understand the shape of the universe.
It really is. It's a perfect example of how mathematics can unlock the deepest secrets of the universe.
Well, I hope everyone listening enjoyed this deep dive into advanced mathematics. It was definitely challenging, but so worth it.
Absolutely. Keep exploring and asking questions and keep diving deep.
And a huge thank you to all of you for sending us this amazing paper. We wouldn't be here without your curiosity and your passion for learning. So until next time, keep exploring. Welcome to another deep dive. Today we're tackling some pretty intense stuff. Yeah, we're diving into Grisha Perelman's work on the Ricci flow.
Oh yeah,
it's
big stuff.
Big stuff. We're looking at excerpts from this paper, the entropy formula for the Ricci flow, and its geometric applications.
Right.
It's not exactly light reading, but the insights are. I think
they're amazing.
They're amazing.
Yeah. Perelman's work is like a Rosetta Stone for understanding the shape of the universe, how it evolves, and singularities, which are fascinating.
Okay, so maybe for our listeners who haven't quite had their coffee yet.
Yeah, let's start with the basics.
Start with the basics. What is the Ricci flow?
Okay, so imagine the universe not as a static picture, but as a movie.
Okay.
Every frame of this movie represents the universe at a different point in time.
Okay.
And the Ricci flow describes how the geometry of the universe, the way we measure distances and curvatures, changes from one frame to the next.
So we're watching space-time itself morph and evolve.
Yeah.
Yeah, okay.
Mathematically, Ricci flow is described by a differential equation.
Right.
It tells us how the metric tensor, which defines distances on a manifold, changes over time.
Right.
This change is driven by the curvature of the manifold.
Yeah, I remember from my Riemannian geometry courses, the metric tensor is really the key ingredient for doing any kind of geometry on a manifold.
Exactly.
It lets us measure lengths, angles, volumes.
Yeah.
So the Ricci flow is telling us how all of those geometric quantities are changing.
You got it.
Over time.
One of the early pioneers in understanding Ricci flow was Richard Hamilton.
Really?
He proved the short time existence of solutions to the Ricci flow equation.
Right.
This means that given any smooth initial metric, the Ricci flow equation has a unique solution, at least for a short period of time.
So we know that it makes sense, at least for a little while.
For a little while.
But what about the long-term behavior? Where's this cosmic movie headed?
That's where Perelman's work comes in.
Okay.
And this is where things get really fascinating.
Okay.
He showed that the Ricci flow isn't just some arbitrary process. It's actually a gradient flow.
A gradient flow. Now, didn't we encounter those in multivariable calculus?
Exactly, yeah.
It's like a ball rolling down a hill, always seeking
That's a good analysis.
the lowest point.
Yeah, a gradient flow is a system that evolves to minimize a specific energy functional.
Okay.
And Perelman's breakthrough was discovering a particular functional which decreases along the Ricci flow.
So it's like the universe is trying to find its most relaxed state.
Exact.
The state of minimum energy.
Exactly.
Through this Ricci flow process.
Yeah, and this insight opens up a whole new way.
Okay, of understanding the long-term behavior of the Ricci flow.
Right.
It allows us to analyze its evolution using tools
Okay.
from the calculus of variations
Right.
and geometric analysis.
Okay, I'm hooked. This special functional Perelman discovered, is it something we can actually write down?
Yeah, we can write it down.
Or is it one of those?
It's definitely not a simple object, so
Yeah.
we can write it down
Me
and break
too.
it down piece by piece.
Right.
So it's defined for a Riemannian metric,
Okay.
which is denoted by GIG,
Okay.
and a function $5 on a closed manifold, which we'll call $1.
Okay.
The functional, which we denote by $5,
Okay.
is given by the following integral.
All right.
I plus nabla F2 E-F.
DVA.
Okay, let's unpack this equation.
All right.
I see the integral sign, which means we're summing up something over the entire manifold, null or dollar.
Right.
What's inside that integral?
Inside, we have a few key players.
Oh.
First, we have $4, which represents the scalar curvature of the manifold.
Right.
It's a measure of how much our space is curved at each point.
Right. Scalar curvature. That's a fundamental concept in
Yes.
Riemannian geometry.
Exactly.
It's a single number at each point that
Yeah.
tells us
How much our space is bending.
how much our space is bending. Yeah.
Then we have nabla fall,
Okay.
which represents the gradient of the function fall doll.
Okay.
This tells us how falls is changing in different directions on the manifold.
So it's like the directional derivative. somewhere.
Precisely. Next, we have Leverard term involving the exponential function
Right.
applied to this. This function, full dollar, plays a role similar to what physicists call a dilaton field.
Okay.
It's a function that helps us understand how volumes change under
Right.
the Ricci flow.
Okay.
And finally, we have d valor,
Right.
which is the volume element of our manifold.
Yes.
It tells us how to integrate over volumes in our curved space.
So to put it all together,
Yeah.
the value of this functional dollar
Right.
depends on the geometry of our space.
Yeah.
Encoded in the scalar curvature.
Yes.
The behavior of this dilaton field, $5,
Wow.
and how volumes are measured.
You got it.
This is where my brain starts to hurt a bit.
I know.
What's so special about this particular combination of terms?
Yeah, it's a great question.
Why does it decrease under the Ricci flow?
The answer lies in some beautiful but somewhat technical mathematics.
Okay.
The key is to look at how $5 changes with time
Right.
as the metric evolves under the Ricci flow.
Right.
It turns out that its time derivative can be expressed in terms of something called the 202 gradient of the scalar curvature, $2.
Okay, now you're just showing off with all these fancy mathematical terms.
Pretty little.
But seriously, can you give us a sense of what this 202 gradient is?
Right, so the 203 gradient is a way of measuring
Yeah.
how much the scalar curvature dollar is changing in
Okay.
different directions on the manifold. And what's remarkable is that the time derivative of dollar turns out to be negative, which means
Like-
dollars is always decreasing.
So it's like we have a mathematical guarantee
Yes.
that this energy
Yeah.
of the system is always decreasing, like that ball rolling down a hill.
Yes, exactly.
But how do we know that this functional $5
It's a very insightful question.
is the right one to look at?
Yeah.
Could we have chosen a different functional,
It turns out
a different energy?
that the choice of this functional
Okay.
is closely tied to the concept of entropy, which is where Perelman's work takes us to
Wow.
a whole new level of understanding.
Entropy. Isn't that something to do with thermodynamics
Yes.
and the disorder of a system?
Yeah.
What does that have to do with the geometry of the universe?
That's what we'll dive into next.
Okay.
The connection between entropy, geometry, and the Ricci flow
Right.
is one of the most beautiful and unexpected discoveries in modern mathematics.
Okay, now I'm really intrigued. But before we jump into that, can we go back to this idea of the functional find dollars for a moment?
Yeah.
You mentioned something about a dilaton field and how different choices of dollars could lead to the same flow, just up to a diffeomorphism?
Does sound like magic.
Yeah, it sounds a bit like mathematical magic.
But it's actually a very deep and subtle point.
Okay.
It has to do with the fact that when we talk about the gradient flow for $5,
Right.
we are implicitly assuming a fixed volume form.
Right, the volume form tells us how to measure volumes in our curved space.
Exactly.
Okay.
But we could choose a different volume form
Right.
and consider the gradient flow for $5
Yeah.
with respect to this new volume form.
Okay.
What's remarkable is that this new flow
Okay.
will be the same as the original flow
Right.
up to a diffeomorphism.
Wait, remind me what a diffeomorphism is again?
Oh, yeah. A diffeomorphism
It's been a while since my topology classes.
is essentially a smooth, invertible transformation of our space. You can think of it like stretching or bending a sheet of rubber without tearing it.
Okay, I'm picturing it.
Yeah.
So are you saying that choosing a different Dilaton field,
Yeah.
$5,
That's a great way to put it.
is like choosing a different way to measure volumes?
The choice of $5 is, in a sense, a choice of gauge.
Okay.
Like choosing a particular coordinate system to describe a physical phenomenon. The underlying geometry and the evolution under the Ricci flow remain the same.
This is fascinating.
It is.
So we have this beautiful connection between the Ricci flow, this energy functional, $5, and the choice of a gauge represented by the Dilaton field.
Yeah.
It's like we're peeling back the layers of an onion, revealing deeper and deeper levels of structure.
That's a great analogy.
But I still have to ask, where does the entropy formula fit into all of this?
You're absolutely right. We've been setting the stage to understand Perelman's entropy formula. It takes this gradient flow perspective to a whole new level.
Okay.
Essentially, it introduces a new functional, which we'll call dollar, that generalizes the functional dollars we've been discussing.
Okay, so it's like we're taking everything we've learned about $5 and cranking it up a notch.
Yes, exactly.
Give us a taste of what this dollar functional looks like and why it's so important.
Well, dollars is a bit more complicated than $5, but it explicitly incorporates a scale parameter, which we'll denote by tout. This scale parameter is crucial because it allows us to analyze the Ricci flow at different levels of detail, like zooming in and out of our cosmic movie.
Okay, so it's like we're adding another dimension to our analysis.
Exactly.
Literally.
Yes.
Okay. But before we dive into the details of dollars, I think it's time for a quick
break.
We'll be back soon to explore the mysteries of Perelman's entropy formula and its implications for understanding the universe.
Yes. Welcome back. Before the break, we were discussing this concept of the Ricci flow as gradient flow, seeking to minimize a special energy functional. This functional, which we labeled $5, gave us a really powerful way to analyze how the geometry of the universe changes under the Ricci flow. But as we hinted at, the story doesn't end there. Perelman took this idea even further with his concept of entropy for the Ricci flow, introducing a new functional, $1.
You mentioned this dollar functional incorporates a scale parameter, tau tau akka. Why is that so important? And how does it relate to the concept of entropy, which usually evokes ideas from thermodynamics?
Excellent questions. Let's start with the scale parameter. Imagine you're looking at a map of a city. If you zoom in, you see the details of streets and buildings. If you zoom out, you see the overall layout of the city and its surroundings. The scale parameter acts in a similar way for the Ricci flow. It allows us to analyze the flow at different levels of detail. A large tau gives us a large-scale view, while a small tout lets us zoom in on the finer details of how the geometry is changing.
I'm starting to see how the scaling could be useful. But how does it connect to the concept of entropy?
So the connection lies in the fact that as the Ricci flow evolves, the geometry of the universe can become quite complex. Think about wrinkles forming on a smooth surface, or the intricate patterns of a flowing river. Entropy, in a sense, measures the complexity of these patterns. In thermodynamics, entropy is often associated with disorder. But it's more accurate to think of it as a measure of how much information is needed to describe the state of a system.
So a more complex, wrinkled geometry would have higher entropy as a smooth, uniform geometry.
And Perelman's brilliance was in finding a way to quantify this notion of geometric complexity using his entropy formula.
I'm on the edge of my seat here. What does this formula actually look like? Is it as intimidating as that functional dollars that we saw earlier?
It is a bit more intricate, but it builds upon the ideas we've already discussed. Here it is. Dollar deliri f tau, ntm, ntm tau plus fm4 dash n2 e of e.
I see some familiar faces in there. The scalar curvature, the gradient of the Dilaton field, and the volume element, dz of e. But we also have this scale parameter tau sprinkled throughout the equation. And what's with that term, 40del2? It looks a bit like something from a physics textbook.
You have a sharp eye. That term is indeed inspired by physics, specifically from the study of heat diffusion. It turns out that the Ricci flow has a deep connection to the heat equation, which describes how heat flows through a material over time.
Wow, now that's a surprising connection. I never would have guessed that the evolution of the universe's geometry would have anything to do with heat.
It's one of those beautiful and unexpected links that make mathematics so fascinating.
Yeah.
But to go back to that entropy formula, the key idea is that under a particular set of evolution equations, which include the Ricci flow, this functional dollar is always non-decreasing.
Non-decreasing. So it can increase, but it can never go down.
Yes.
That sounds a lot like the second law of thermodynamics.
Exactly.
Which states that the entropy of a closed system never decreases.
And that's why we use the term entropy in this context.
Okay.
It's not about heat or disorder in the usual sense, but it's a quantity that captures something fundamental about the evolution of the universe's geometry under the Ricci flow.
This is mind-blowing. So we have this deep analogy between the Ricci flow, which shapes the universe's geometry, and thermodynamics, which governs the behavior of heat and energy.
It's like we're seeing two different sides of the same coin connected by this concept of entropy. But there's still one piece of the puzzle we haven't fully addressed. Singularities. These are the points where the curvature of space-time blows up, like at the center of a black hole. How can we even talk about a functional like dollars being non-decreasing if we have these singularities potentially wreaking havoc?
That's a great question. Singularities have always been a thorn in the side of physicists and mathematicians. They represent these points.
Points where our usual laws of physics break down. And this is where Perelman's work truly shines. He was able to make sense of these concepts, even in the presence of singularities.
So he found a way to smooth over those wrinkles in space-time.
Not exactly smooth over, more like he found a way to understand their behavior and control their impact. And that's where the concept of kappa non-collapsing comes in, which we mentioned earlier.
You mean the idea that even near a singularity, the volume of space-time can't shrink to zero. It's like there's a fundamental thickness or a quantum foam that prevents complete collapse.
This non-collapsing property is crucial for ensuring that the entropy, as defined by Perelman's formula, remains well-behaved, even as the Ricci flow approaches a singularity. It sets a limit on how much disorder or complexity can accumulate, preventing the universe from imploding into a point of infinite entropy.
That's incredible. It's like Perelman found a way to tame these wild singularities, putting them on a leash so that they can't completely disrupt the flow of the universe.
Exactly.
It's truly remarkable how all these pieces fit together, from the gradient flow picture to the concept of entropy and this non-collapsing property.
It all fits together.
But to be honest, I'm starting to feel a bit overwhelmed by all these mathematical details.
Yeah, it can be a lot.
Can we take a step back and try to understand Perelman's entropy formula?
Sure.
On a more intuitive level.
Absolutely. Sometimes stepping away from the equations can provide more clarity. Let's try to understand it in terms of a statistical analogy, which might sound a bit surprising.
A statistical analogy, you mean like rolling dice or flipping coins?
Well, not exactly coins or dice, but the idea is that we can think of the Ricci flow as being analogous to a physical system evolving over time. And in this analogy, Perelman's entropy formula is related to something called the partition function in statistical mechanics.
I vaguely remember the partition function from my thermodynamics courses. Can you remind me what it is?
Sure.
And how it connects to the Ricci flow?
The partition function, often denoted by Zella, is a fundamental concept in statistical mechanics. It's essentially a sum over all possible states of a system, weighted by their energies. It's a powerful tool that allows us to calculate macroscopic properties of a system. Like its temperature, pressure, and entropy, from the microscopic details of its constituent particles.
So if we have a container of gas molecules bouncing around, the partition function tells us about all the different ways those molecules could be arranged and how likely each arrangement is.
Exactly. And the key insight is that we can apply a similar idea to the Ricci flow. In our analogy, the metric, or the shape of our universe, represents the state of our system, the Ricci flow, which describes how the metric changes over time, represents the evolution of the system.
Okay.
And Perelman's entropy formula
Yeah.
can be expressed in terms of a partition function-like quantity
Okay.
that sums over all possible geometries of the universe.
So instead of summing over states of gas molecules,
Yes.
we're summing over different shapes of the universe.
You got it.
Wow.
And just like in statistical mechanics, where different states have different energies, in Perelman's formula, different geometries have different weights
Okay.
determined by the functional dollar.
Right.
It's like assigning a probability to each possible shape of the universe.
Wow. So it's like we're taking a statistical average
That's a good way to think about it.
over all possible shapes of the universe.
And in this picture, Perelman's entropy formula tells us how this average shape evolves over time
Okay.
under the Ricci flow.
Okay.
It's a beautiful connection between geometry and statistical mechanics
Yeah.
that gives us a whole new way to understand the Ricci flow.
This statistical analogy is really helpful in grasping the essence of Perelman's work. It's like we're seeing the Ricci flow not just as a geometric process, but as a statistical phenomenon.
Exactly.
Where different shapes of the universe are competing for dominance.
And this competition is guided by the entropy,
Right.
which, as we've seen, has this fundamental property of never decreasing. It's a profound insight that connects the evolution of the universe with the deep principles of statistical mechanics.
Right.
We've covered a lot of ground today.
We have.
And I think it's time to take another short pause.
Okay.
When we return, we'll explore yet another perspective on the Ricci flow,
Okay.
this time through the lens of higher dimensional geometry. Stay tuned.
Welcome back.
Whee!
We've been on quite a journey exploring the Ricci flow,
Yeah.
from its basic definition to its connection with entropy
Yeah.
and the remarkable work of Grisha Perelman.
Right.
Now, I understand we're taking things up a notch,
A little bit. Yeah.
venturing into the realm of higher dimensional geometry.
Yes.
To be honest, this is where I usually start to feel a bit lost,
Okay.
but I'm trusting you to guide us through it.
I'm happy to be your guide.
Okay.
Sometimes to understand a concept deeply, we need to step outside our usual frame of reference and view it from a different perspective. That's what we'll do now. By exploring how the Ricci flow can be viewed within a larger, higher dimensional space.
Okay, this sounds intriguing,
Yeah.
but also a bit daunting.
It can be.
We're already dealing with the universe that's expanding and evolving in 4 dimensions, time and the 3 spatial dimensions.
Right.
How can adding even more dimensions possibly make things clearer?
It might seem counterintuitive, but sometimes going to higher dimensions can actually simplify things.
Okay.
Think about how a shadow,
Yeah.
which is a 2-dimensional projection of a 3-dimensional object,
Right.
can sometimes reveal features of the object that are difficult to see directly.
Okay, I'm starting to see the analogy.
Yeah.
So we're essentially trying to find a higher dimensional shadow of the Ricci flow
That's it.
that will reveal some hidden structure.
And the key idea is to view the Ricci flow as happening not just within our usual space-time,
Okay.
but on a Riemannian manifold,
Right.
a higher dimensional space with its own geometry.
I remember from my Riemannian geometry courses that manifolds are like generalizations of surfaces,
Yeah.
but they can have any number of dimensions.
Right.
So are we picturing the Ricci flow as happening on something like a sphere
It could be a sphere,
or a torus?
a torus, or something much more complicated.
Okay.
The specific shape of the manifold isn't as important as the fact that we can equip it
Okay.
with its own Riemannian metric, its own way of measuring distances and curvatures.
So it's like we're adding another layer of geometry
Yes.
on top of the already curved geometry of the universe.
Exactly.
This is starting to sound like a recipe for a mathematical headache.
It might sound complicated, but trust me, it's worth the effort.
Okay.
By studying the geometry of this larger space,
Yeah.
we can gain profound insights into the behavior of the Ricci flow.
Okay. I'm willing to give it a shot.
All right.
But how do we even construct this higher dimensional space? What are the ingredients?
Okay, let's build it up step by step.
Okay.
We start with our usual space, the 3-dimensional manifold dollar
Right.
that represents our universe at a fixed point in time.
Okay.
Then we add the dimension representing the scale parameter,
Right.
giving us a 4-dimensional space, denoted by dollar times math plus $.
Okay. So far, so good.
Okay.
We've got our universe, $dollar,
Yeah.
and we've added the scale parameter, tau,
Yes.
as an extra dimension.
As an extra dimension.
What's next?
Now comes the interesting part.
Okay.
We introduce another ingredient into our recipe.
Okay.
A high-dimensional sphere.
Okay.
Denoted by 70 Noller,
Okay.
where Nollers is a very large number.
Hold on. Why a sphere?
The sphere
And why does it have to be so high-dimensional?
plays a special role in helping us understand the geometry of this larger space.
Okay.
It's a compact, symmetrical object
Okay.
with well-understood curvature properties,
Right.
and we need it to be high-dimensional
Okay.
to capture the complexities of the Ricci flow,
Right.
which, as we've seen, can lead to very intricate and even singular geometries.
Okay. I'm willing to suspend my disbelief for now.
All right.
So we'll get this Frankensteinian space.
Yeah.
1 times Sn times math BRB.
Right.
It's a mix of our universe.
Yeah.
A high-dimensional sphere
Yeah.
and the scale parameter all stitched together.
Right.
Seems strange.
It might seem like a strange concoction at first glance,
Yeah.
but the key is to define a special Riemannian metric on this space,
Okay.
a way of measuring distances
Right.
that takes into account the geometry of each component.
Right.
This metric is built from the metric on Noller,
Okay.
which is evolving under the Ricci flow,
Okay.
the standard metric on the sphere, $7,
All right.
and a factor involving the scale parameter, tau.
So the geometry of this higher dimensional space is directly linked
Precisely.
to the geometry of our universe.
Yes.
And how it's changing under the Ricci flow.
And here comes the truly remarkable part.
Okay.
With the right choice of metric, this larger space becomes Ricci flat.
Wait, zero curvature.
That means it's Ricci curvature,
Okay.
which is a measure of how much the space is curved,
Right.
is identically zero everywhere.
But we're talking about the Ricci flow,
I know, it seems paradoxical.
which is all about curvature. How
Wow.
can a space that's supposed to capture the dynamics of curvature
But that's the beauty of it.
to be flat?
By embedding our curved universe
Yeah.
into this larger Ricci flat space,
Yeah.
we gain a fresh perspective on the Ricci flow.
Okay.
It's like viewing a curved line drawn on a flat sheet of paper.
Right.
The flatness of the paper helps us understand the curvature of the line
Right.
by providing a reference point.
That's a great analogy.
Yeah,
But I'm still struggling to wrap my head around the fact that this larger space,
sure.
even with its high-dimensional sphere and extra dimensions,
It takes some getting used to.
is actually flat.
But one way to appreciate the power of this construction is to consider something called the Bishop-Gromov volume comparison theorem.
Okay, so we're going even deeper into the realm of geometry now.
Indeed.
Okay.
The Bishop-Gromov theorem is a powerful tool that allows us to relate local and global geometric properties.
Okay.
And what's remarkable is that it applies beautifully
Yeah.
to our Ricci flat Frankensteinian manifold.
Okay.
By applying this theorem,
Yeah.
we obtain a new monotonicity formula for the Ricci flow,
Okay.
distinct from the entropy formula we discussed earlier,
Right.
but equally profound.
So we have yet another quantity
Yes.
that's always increasing or staying the same
Yes.
as the Ricci flow evolves.
Yes.
What does this new formula tell us about the universe?
This new formula involves a quantity called the reduced volume,
Okay.
which in a sense measures volumes in our universe from the perspective of this larger Ricci flat space. It's
Right.
like having a bird's eye view of the flow,
Right.
seeing how it shapes the universe at different scales and over vast stretches of time.
Right.
And just like the entropy formula, this
Yeah.
new monotonicity formula plays a crucial role
Okay.
in understanding the formation of singularities
Right.
and the long-term behavior of the Ricci flow.
So Perelman's work not only gave us the entropy formula,
Right.
but it also opened up this whole new way of looking at the Ricci flow.
Exactly. His work was truly groundbreaking.
Yeah.
It provided us with new tools and concepts to understand one of the most fundamental processes shaping the universe.
Right.
And it has opened up new avenues of research
Right.
that continue to yield exciting discoveries.
It's been an incredible journey exploring Perelman's work and the Ricci flow.
It has.
We've traveled from the basics of Riemannian geometry to the depths of entropy,
We have.
and even into the realm of higher dimensional spaces.
Higher dimensions.
It's amazing how mathematics can provide such profound insights into the workings of the universe.
I couldn't agree more. And while we've learned a great deal, there are still many mysteries to unravel.
Right.
What other secrets does the Ricci flow hold?
Yeah.
What new connections between geometry, physics,
Right.
and even other fields remain to be discovered?
Yeah.
These are questions that will keep mathematicians and physicists busy for generations to come.
Well, on that note, I think it's time to wrap up this deep dive.
Okay.
I hope you, our listeners, have enjoyed this exploration into the fascinating world of the Ricci flow and the groundbreaking work of Grisha Perelman.
Until next time.
Until next time.
Keep exploring.